Hi everyone, welcome to Go Classes. In this lecture, we are going to study pumping lemma for regular languages. What is this pumping lemma? So we will do the complete analysis of pumping lemma. So let's start now. In this pumping lemma for regular languages, what we are going to study? These are the things that we will study. First, we will see what is pumping lemma. We will take many examples. Then we will study the proof of pumping lemma. What is the proof? This proof we will study. And we will see some examples which are based on the proof. Based on the proof, also some questions can be created. If you don't know the proof, then these questions you will not be able to solve. Okay. So remember this point. Based on the proof, some questions can be created. Those questions also we will see. We will see how to find minimum pumping length for a regular language. We will also study how to prove that a language is non-regular using pumping lemma. Using this, we will learn how to prove that a language is non-regular. We will also see some important and useful results, some helpful results we will see. Then we will see some non-regular languages which will satisfy pumping lemma. Okay. So this is this is the overall structure of this pumping lemma that we will study. These are the concepts that we will study in this pumping lemma. Okay. So let's start now. In this lecture, what we are going to study? In this lecture, we will study what is pumping lemma, finding minimum pumping length, also proving that a language is non-regular. Okay, so these are the three concepts that we will study in this lecture. Okay, the remaining concepts we will see in the next lecture. So let's start this lecture now. Now, before starting this pumping lemma, let me tell you some things about this pumping lemma. This is one of most complicated topics in theory of computation. Okay, in this theory of computation in TOC, this pumping lemma is one of the most complicated topics. Many students, or I can say majority of students, they don't understand this pumping lemma. Okay, so the best way to understand this pumping lemma is to work it out. So take your copy pen. Don't watch this video like a movie. If you truly want to understand this pumping lemma, if you really want to understand what is this pumping lemma, and if you want to be expert of this pumping lemma, whatever question comes in any exam, if you want to solve it, then please take copy pen. Don't watch this video like a movie. Take a copy pen, okay, and do it. Whatever question I give to you, whenever I am solving any question, you also solve that question. Okay, so that is the best way to understand this pumping lemma. So did you take your copy pen? Don't watch this video like a movie, because I am telling you pumping lemma, this is one of the most misunderstood concepts of theory of computation, most complicated topic in theory of computation, and majority of students, they don't understand this. So take a copy pen and let's do it. Let's understand this pumping lemma. So let's see this chapter 1. In this chapter 1, we will see what is pumping lemma. What is this pumping lemma? So the name is, I can say the name is quite fancy, right? Pumping lemma. The name is very fancy. So let's see what this means, pumping lemma. So let me tell you, what is a lemma? What is a lemma? Lemma is a theorem. Lemma is, I can say it is a mini theorem. You can say that lemma, that is a theorem. Okay, so you have to prove it. Yes or no? Lemma is a theorem. Theorem means you need to prove it. Okay, what is a theorem? Theorem means it is proven to be true. It is proven to be true. Okay, so remember, we have to prove this pumping lemma. Whatever I will teach you, we need to prove it. So this lemma, this is a mini theorem. You can see. Okay, so you can see what is a lemma. If this is a theorem, then mini theorem, that will be lemma. Okay, so lemma is saying I'm mini. So very simple. So this is the idea. So you can see this. What is a lemma? Lemma is basically a little theorem, or I can say mini theorem. But anyway, no one will ask you what is theorem, what is lemma, what is the difference between theorem and lemma. No one will ask you. In any exam, they will not ask you what is the difference between theorem and lemma, because actually there is no difference. Actually, you can notice there is no difference. Basically, there is no formal difference. There is no formal distinction between lemma and theorem. So you can simply say that lemma is basically just small theorem. Okay, very simple. So anyway, the point is this lemma is a theorem. So we need to prove it. Whatever I will tell you, whatever I will teach you, we will prove also. Okay. So what is this pumping? This we will study pumping, but this pumping basically means repetition. this pumping, this basically means repetition. Okay, repetition any number of times, 0 or more times. This means repetition any number of times, any number greater than or equal to 0, any number of times. Okay, you are repeating something any number of times. You tell me something. You tell me, if I give you this string, for example, let me give you this string AB. If I repeat this string 0 times, then what I will get? For example, if I say that if I repeat this string 0 times, repeat this string 0 times, 0 times means AB power 0. Okay, so I will get AB power 0, that will be empty string. So if I repeat this string 0 times, then I will get empty string. If I repeat this string 2 times, what I will get? If I repeat this string 2 times, means AB power 2, AB power 2, I will get AB, AB. If I repeat this string 1 time, what I will get? If I repeat this string 1 time, what I will get? I will get AB. Okay, so anyway, the point is, what is pumping? This pumping simply means repetition. Repetition any number of times, 0 or more number of times. You can repeat 0 number of times. If you repeat 0 number of times, then basically this string is gone. Yes or no? This string is gone. If you repeat this 0 number of times, then basically this string is gone. If you repeat it 2 number of times, then you will get this. If you repeat it 4 number of times, then what you will get? 4 number of times. If you repeat 4 number of times, you will get AB, 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 AB. If you repeat 4 number of times. So the point, did you understand the point? That what is pumping? Pumping means repetition. Lemma means mini theorem. Okay. Next, for regular languages means this pumping lemma, this is a theorem. This is a repetition theorem for regular languages. Okay, I hope this point is clear. So what I'm saying? I am saying that this pumping lemma, this is a theorem for regular languages. So this is the point. This is the ultimate point, that this pumping lemma for regular languages. For regular languages. What this means? This is a property, or I can say this is a theorem. This is a theorem for regular languages. So remember, for regular languages, this pumping lemma, this is a theorem which is satisfied by regular languages. Okay, so ultimately this pumping lemma, this is a theorem. This is a statement which is true for all regular languages. So ultimately I can say this pumping lemma. What is this PL? This PL means pumping lemma. In short, I'm writing. Okay, this pumping lemma, in short, I'm writing PL. So this pumping lemma is a statement. This pumping lemma is a statement, or I can say this is a theorem. Okay, this is a statement which is true for all regular languages. Which is true for all regular languages. Okay, is this point clear? I'm just telling you what it means. See, so far we did not study what is pumping lemma. We did not see what is this statement. Yes or no? Did I tell you what is this statement? No, I did not tell you what is this statement, but I am saying that this pumping lemma, this is just a statement. So this pumping lemma, this is basically a statement. It is basically a statement which is true. This statement is true for all regular languages. Okay, this statement, this is true for every regular language. For every regular language. Is this point clear? Tell me. So far we did not study what is this statement. Okay, so far this statement, what is this statement, that we did not see. But I am telling you that this pumping lemma, this is a statement. This is a statement which is true for all regular languages. So that is the reason. What is the name of the topic? What is the name of the chapter? The name of the chapter is pumping lemma for regular languages. Is this point clear? So far, did you understand this? What is pumping lemma? So ultimately, let me tell you, this is pumping lemma on your screen. On your screen, this is pumping lemma. Means what I'm saying here, what you have to write this statement. What is this statement? What is this pumping lemma? This pumping lemma is a statement. This pumping lemma is a statement which is true for all regular languages. But what is this statement? What is this statement? This is the statement. Looks complicated, right? Yes or no? Looks complicated, but don't worry, we will study this. So far, don't worry about this. Okay, do not worry about it. But I am telling you that pumping lemma is a statement. This statement is true for every regular language. Is this point clear? Please tell me. Remember this statement, this is pumping lemma. This statement is pumping lemma. And this statement is true. This statement is true for every regular language. So this is the point. Okay. Now let's move on. Now let's see one analogy to understand. One analogy I want to tell you from the number theory. You tell me the answer for this question. I'm just telling you one analogy so that we can understand some concepts that I am going to teach you. So first, tell me the answer for this question. Which property is satisfied by even numbers? Tell me, which property is satisfied by even numbers? So yes, multiple of 2. This property is satisfied by even numbers. Can I say this property is satisfied by even numbers? Can I say this property is satisfied by even numbers? Can I say? The answer is no. What is the counterexample? Can you give me counterexample? Can you give me counterexample? So the answer is no. This property is not satisfied by. Can you give me counterexample? For example, 6. 6 is not multiple of 4. For example, 2 is not multiple of 4. For example, 10 is not multiple of 4, and so on. Okay, so these are the counterexamples. So can I say this is not a property of even numbers? If someone asks you property of even numbers, then will you say that they are multiple of 4? Will you say? If someone asks you property of even numbers, then will you say that they are multiple of 4? No, you will not say. But you can say they are multiple of 2 because every even number is multiple of 2, right? Yes or no? Because the point is every even number satisfies. Every even number satisfies this property. Okay, so this is the idea. Now tell me the answer for this question. Tell me the answer. Which property is satisfied by prime numbers? Which property is satisfied by prime numbers? Which property is satisfied by prime numbers? Is it satisfied by prime numbers? Is it satisfied by prime numbers? No, this is not satisfied by prime numbers. What is the counterexample? This property is not satisfied by prime numbers. What is the counterexample? For example, the counterexample is 11. 11 is prime but not even. 11 is a prime number but not even. Can I say that? Can I say every prime number is odd? Can I say every prime number is odd? This property is also not satisfied by prime numbers. So if someone asks you, give me a property of prime numbers, will you say that they are odd? Will you say? If someone asks you that give a property which is satisfied by prime numbers, give a property which is satisfied by prime numbers, will you say that they are odd? Will you say? No, you will not say, because what is the counterexample? Tell me, what is the counterexample? The counterexample is 2. The counterexample is 2 because 2 is prime. 2 is prime, and you can notice that 2 is not odd. 2 is prime and 2 is not odd. So this is the counterexample. So remember, none of them is a property of prime numbers. Now tell me the answer for this question. Which property is satisfied? Which property is satisfied by prime numbers greater than equal to 2? Prime numbers greater than equal to 2. Now the answer will be being odd. Okay, now the answer will be being odd because every prime number greater than equal to 2 satisfies this. I can say every prime number, whatever prime number greater than equal to 2 you take, that will satisfy this. Satisfies it. Yes or no? Satisfies it. Very simple. Tell me the answer for this question. Tell me the answer. Which property is satisfied by prime numbers? Which property is satisfied by prime numbers? So this is not satisfied by prime numbers. The counterexample is 2. Okay, this is not satisfied by the prime numbers. The counterexample you already know. The counterexample is 2. This is not satisfied by prime numbers. The counterexample, for example, 11, that is the counterexample. What about this? What about this? Is this satisfied? Is it satisfied by every prime number? Like every prime number P will satisfy this. Every prime number P will satisfy this. Whatever prime number P you take, it will be true. For every prime number, this will be true, right? Yes or no? For every prime number. For every prime number, it is satisfied. It is true. It is true. You can check. Okay, whatever prime number you take, that will be true. For example, you can take any prime number. You can take any prime number. You can easily notice this P plus 7. This will be not prime because you can notice, for example, if you take this prime number, then P plus 7 is 9. And you can notice that is not prime. And you can notice that is not prime. Similarly, you can notice the remaining primes are odd. Yes or no? the remaining prime numbers, they will be odd, correct? The remaining prime numbers will be odd. If you do odd plus 7, if you do odd plus odd, that will be even. If you do odd plus odd, that will be even. Okay, that will be even. And definitely even greater than 2, that will be even greater than 2. Okay, that will be even greater than 2. Even greater than 2 is never prime. Yes or no? Even number greater than 2 is never prime. Even number which is greater than 2, that is never prime. So you can easily notice this option C. Can I say this is a property of prime numbers, all the prime numbers? This is a property of all the prime numbers. Yes or no? This is a property of all the prime numbers. Is this understood? Please tell me. This is the property of every prime number. So very easy. So you can see. Now let's move on. Now let's come back to this example again. Tell me the answer again, just one more time. Tell me the answer one more time. Which property is satisfied by prime numbers greater than 2? The answer is being odd. This property is satisfied. Okay. Now you tell me one thing. Now you tell me one thing. So all the prime numbers greater than 2 will satisfy this property. All the prime numbers. Which of these two statement is true? See what I'm saying. I'm saying every prime number greater than 2 will satisfy this property. Let's call this property P. Let's assume that this property is P. Okay. This is what I'm saying. I'm saying that let's assume this property is P. P means being odd. Okay. This is property P. Now tell me which statement is true. Which of the following statement is true? Every prime number greater than 2 satisfies property P. Can I say? Your property P is being odd. Being odd. This is the property P. Can I say every prime number greater than 2 satisfies property P? Yes. Yes or no? It is true. But what about this one? If property P is satisfied by a number, then can I say it is a prime number greater than 2? Can I say if this property is satisfied by a number, then can I say that number is a prime number greater than 2? No, we cannot say. What is the counterexample? What is the counterexample? For example, you can notice 9. Okay, for this, what is the counterexample? The counterexample is 9. You can take n equal to 9. You can take this. You can easily notice this. For this property P is satisfied. This property P is satisfied, but you can notice that this is not a prime number. But you can easily notice this is not a prime number. Okay. So what I want to say, finally, let me tell you what I want to say. I want to say that basically, this is what I want to say, that if you take any prime number greater than 2, then that will definitely satisfy. Remember, every prime number, whatever prime number you take, every prime number greater than 2, that will definitely satisfy property P. Yes or no? That will definitely satisfy property P. But some other people also can satisfy property P. Yes or no? Is this correct? See, every prime number greater than 2, that will satisfy property P. But what I'm saying that some other person also can satisfy property P. Or I can say that if you don't take prime number greater than 2, then this property may or may not be satisfied. So this is what I want to say, that every prime number greater than 2, that will satisfy property P, but some other people also can satisfy. Yes or no? Some non-prime numbers also can satisfy. Some non-prime numbers, they can also satisfy. They also satisfy. So understand the difference between every and some. Here we are using the word every. Here we are using the word some. Is this correct? So did you understand this? Some number. So what is that some number? What is that some number? For example, tell me, give me a number which will satisfy property P. For example, you can take 9. For example, you can take 9. Okay. And here you can notice that every prime number greater than 2 will satisfy property P. Okay. So far, is it clear? So this is the point. This is the point, that this is your property. Look at this. This is your property being odd. Every prime number greater than 2 will satisfy. Okay. Whatever prime number you take, that will definitely satisfy. But you can notice some non-prime numbers will also satisfy. Okay. Is this understood? These words are very important. Some, comma, all. These words. So please tell me, so far, whatever we have seen, is this clear so far? Simple examples I am taking. I am building towards our pumping lemma. So far, everything is clear. Tell me. Let me know. Okay, now let's move on. Now let's see this. The same thing actually happens for pumping lemma. Let me tell you, we will prove it, don't worry. But let me tell you, the same thing happens for pumping lemma. See, this pumping lemma is just a statement. This pumping lemma, I told you this pumping lemma, this is just a statement. This is some statement. Okay, this is some statement. Let's call it PL. Let's call it PL. Okay, see, this pumping lemma is just a statement, some statement. This is just a statement. I told you that this is just a statement. We will see what is this statement. We will see. But the point is, this is just a statement. Now, what will happen? We will prove it that every regular language will satisfy this statement. For every regular language, this statement will be true. For every regular language, remember, that will satisfy pumping lemma. Is this point clear? This pumping lemma is a statement, and I am saying that every regular language, whatever regular language you take, every regular language will satisfy pumping lemma. But remember, some non-regular languages also can satisfy. Is this point clear? Some non-regular languages also can satisfy. Some non-regular languages also satisfy. So is this point clear? Let me know. So please understand that every regular language will satisfy pumping lemma. This pumping lemma, this will be satisfied. This statement, this pumping lemma statement, this will be true. This will be true for every regular language. But for some non-regular languages, this pumping lemma will be true. Okay, so this is the idea. Don't worry, we will prove it. Okay, everything that I am telling you, in future we will prove it. But the point is, this is the point, that every regular language is going to satisfy pumping lemma. So you can see, for every regular language, this pumping lemma will be true. This pumping lemma statement will be true. We will prove it. Next, but you can see there are some non-regular languages. They will also satisfy pumping lemma. This also we will prove. Okay. Did you understand so far? Please tell me. This is the idea of pumping lemma. Don't worry. So far, we did not see what is pumping lemma. This pumping lemma statement, we did not see. This statement. This is the main statement, right? Okay. We are going towards it. Don't worry. Okay. We will see this. In future, we will see. But the point is that every regular language will satisfy pumping lemma. For every regular language, pumping lemma will be true. But for some non-regular languages, pumping lemma will be true. Okay. So this is the point. Now tell me the answer for this question. Tell me what is the answer here. Read this question and tell me, is this true or false? True or false? If a language L satisfy pumping lemma, then can I say it is regular? Can I say it is regular? If a language satisfy pumping lemma, can I say it is regular? Can I say it is regular? The answer is no. The answer is no. The answer is no. We cannot say, because I told you, remember I told you some non-regular language also will satisfy. Yes or no? Some non-regular language will also satisfy pumping lemma. There are some non-regular languages, some non-regular languages are there for which this pumping lemma will be true. Okay. So this is the point. Remember, if pumping lemma is satisfied, okay, there is, let's assume this is your language, some language is given to you, and this language, let's assume, satisfies pumping lemma. Pumping lemma is a statement, nothing else. Pumping lemma is a statement, and let's assume L satisfies pumping lemma. L satisfies this pumping lemma. Then remember, it does not mean that it is regular. L satisfies pumping lemma, then I can say L may or may not be regular. L may or may not be regular. L may be regular, L may not be regular. Because some non-regular languages also will satisfy pumping lemma. There are some non-regular languages who can satisfy pumping lemma. Okay. Is this point clear? Yes or no? Some non-regular languages, there are some non-regular languages which will satisfy pumping lemma. So L may or may not be regular. Okay. Next, tell me the answer for this question. Tell me the answer for this one. If a language does not satisfy pumping lemma, if a language does not satisfy pumping lemma, can it be regular? Just tell me this point. Can it be regular? If a language does not satisfy pumping lemma, can it be regular? Can it be regular? No, because every regular language will satisfy pumping lemma. Yes or no? Very simple point. If a language does not satisfy pumping lemma, then can L be regular? Then can L be regular? Tell me this point. Can L be regular? The answer is never. The answer is never, because every regular language will satisfy pumping lemma. This we have already seen that every regular language will satisfy pumping lemma. Satisfies pumping lemma. Okay, so remember, every regular language satisfies pumping lemma. So if a language does not satisfy pumping lemma, then it can never be regular. Yes or no? I can say definitely it will be regular. It will be non-regular. So this statement is true. This statement is true. Is this point clear? So if a language does not satisfy pumping lemma, then definitely it will be non-regular. Then definitely this language is going to be non-regular. Okay, now let's move on. Now tell me about this one. This statement, is this true or false? Satisfying pumping lemma is necessary for regular languages. Satisfying pumping lemma is necessary for regular languages. Is it necessary? Satisfying pumping lemma, is that necessary for regular languages? Yes, of course, that is necessary. Yes or no? That is definitely necessary, because every regular language must satisfy pumping lemma. This is the point. Yes or no? Every regular language must satisfy pumping lemma. So satisfying pumping lemma is necessary for regular languages. Must satisfy pumping lemma. Okay, very simple. So I can say satisfying pumping lemma, that is necessary condition for regular languages. That is true. What about this one? Is this statement true or false? Satisfying pumping lemma is sufficient to say that language is regular. Tell me, satisfying pumping lemma. If you satisfy pumping lemma, is that enough? Sufficient means enough. Is that enough to say that language is regular? The answer is no. The answer is no. This is not sufficient. The answer is this is not sufficient. It is not sufficient. So if you satisfy pumping lemma, that is not sufficient to say that you are regular. Okay? Is this point clear? So very simple. These are the points. Now tell me about this one. Satisfying pumping lemma, can I say that is necessary for non-regular languages? Can I say satisfying pumping lemma is necessary for non-regular languages? Can I say satisfying pumping lemma is necessary for non-regular languages? For non-regular languages. Tell me about this one. Can I say it is necessary? It is necessary. The answer is no. The answer is no, because remember, some non-regular languages will satisfy and some will not satisfy. Okay, so remember, satisfying pumping lemma, that is not necessary for non-regular languages, because remember this point, some non-regular languages will satisfy pumping lemma and some will not satisfy pumping lemma. Some non-regular languages, they will satisfy pumping lemma, and some non-regular languages will not satisfy pumping lemma. Okay, so remember, this is the point, that for non-regular languages, this is not sufficient. This is not necessary. Okay, what about this one? Can I say satisfying pumping lemma is sufficient to say that you are non-regular? Is sufficient to say that you are non-regular? Satisfying pumping lemma, if you satisfy pumping lemma, is it enough to say that you are non-regular? Is it enough to say that you are non-regular? No. No, because all the regular languages also satisfy pumping lemma. Yes or no? Because pumping lemma is satisfied by every regular language and some non-regular language. Is this point clear? Very simple. Yes or no? I hope all these points are clear. All these statements, are they clear? Tell me. So satisfying pumping lemma, is that sufficient to say that you are non-regular? No, that is not sufficient to say that you are non-regular. Okay, very simple. Now, tell me about this one. Pumping lemma. What is this for regular languages? What should I put here? Tell me. What should I put here? So pumping lemma is necessary for regular languages, right? Yes or no? That is necessary for regular languages. Pumping lemma is necessary for regular languages. every regular language must satisfy pumping lemma. So pumping lemma is a necessary condition for regular languages. What about for non-regular languages? What about for non-regular languages? What can you say about non-regular languages? Pumping lemma is, what can you say about non-regular languages? For non-regular languages, this is neither sufficient nor necessary. Okay? Pumping lemma, because remember, some non-regular languages will satisfy, some non-regular languages will not satisfy. So this is neither necessary nor sufficient. Is this point clear? Tell me. Now, tell me one more thing. If I ask you, not satisfying pumping lemma, not satisfying pumping lemma, not satisfying pumping lemma, what can you say? What can you say? Not satisfying pumping lemma. What about that? Can I say not satisfying pumping lemma? Is that necessary or sufficient for non-regular languages? For non-regular languages, not satisfying pumping lemma, can I say it is enough to say non-regular? If you don't satisfy pumping lemma, can I say it is enough? It is enough to say sufficient means enough. So if you don't satisfy pumping lemma, if a language does not satisfy pumping lemma, is it enough to say that it is non-regular? Yes, it is enough. Yes, it is enough. So here the answer will be option B. Okay. So all the variations we have seen. Is this point clear? Please tell me. Let me know. Let me know. Some student is asking, what is the use of this word lemma? What is the use of this word lemma? Pumping lemma. What is the use of this word lemma? So let me tell you. I told you this lemma means mini theorem, right? This lemma means mini theorem. It is a small theorem which is used to prove some other theorem. Okay, so remember this point, pumping lemma, this is just a theorem. This is just a statement which we use to prove other statements. See, what this lemma is used. Let me tell you, actually there is no difference. There is no clear difference between theorem and lemma. I told you. Yes or no? I told you that there is no clear difference. Like for example, in the interview, if they ask you, what is the difference between lemma and theorem? Then you cannot say anything. Okay, because remember in mathematics, there is no clear definition of, or I can say there is no clear difference between lemma and theorem. But what people do, what mathematicians do, they use this word lemma for that theorem which is used to prove other theorems. So remember this lemma, this is just a mini theorem. This is just a mini theorem used in proving other theorems. Used in proving other theorems. Okay, so this pumping lemma, actually this pumping lemma we will use to prove non-regularity. What is the most common use of pumping lemma? See, this pumping lemma is only interesting because it is used to prove non-regularity. See, this most common use of pumping lemma. So this pumping lemma, actually, what is the most common use? We use this to prove non-regularity. So remember, this is used to prove non-regularity of a language. Non-regularity of a language. Okay, so you can see that one thing, you notice one thing, this pumping lemma itself is not useful. Yes or no? For example, this pumping lemma is actually useful whenever you are proving something else. Is this point clear? This pumping lemma is useful whenever you are proving something else. Okay, so this is the point. So that is the reason this is called lemma. Lemma means mini theorem. Again, I am telling you, lemma means mini theorem, small theorem, which is used in proving other theorems. So anyway, don't worry about this lemma. You can call it theorem. No one will cut your marks. You can call it pumping lemma. You can call it pumping theorem. No one will cut your marks. Don't worry. You can call it pumping theorem. No one will question. Okay. So this is also correct, because actually in mathematics, there is no formal difference between lemma and theorem. This I told you. I have shown you the screenshot. Okay. So you can call it pumping theorem. No problem. No problem. You can call it pumping theorem. You can call it pumping lemma. But mathematicians, what they do, they call it pumping lemma. They call it pumping lemma because it is used to prove non-regularity. Means the usefulness of pumping lemma is to prove something else. Okay, we are using it to prove some other theorem. We are using this theorem to prove some other theorem. So that is the point. remember, you can call it pumping theorem. There is no problem. So you can call it pumping theorem. There is no problem. Okay. There is no problem. You can call it pumping theorem. Okay. So whether you call it pumping lemma, whether you call it pumping theorem, that does not matter. Okay. Let's move on. Now tell me about this one. Is this true or not? If a language L satisfy pumping lemma theorem, see, I'm also calling it theorem. Okay. Yes or no? You can see, you can notice, I'm also calling it theorem. So anyway, if a language satisfy pumping lemma, we can say L is regular. The answer is no. Okay. The answer is no. So now this is the note. Can you notice that? Can you notice? Using pumping lemma, can you ever say that a language is regular? Using pumping lemma, can you ever say that a language is regular? No, you can never say. You can never say. But using pumping lemma, you can say that a language is non-regular. Yes or no? For example, if a language does not satisfy pumping lemma, you can say it is non-regular. You can notice. If a language does not satisfy pumping lemma, does not satisfy. Okay. So if a language does not satisfy pumping lemma, then definitely you can say non-regular. But if you satisfy pumping lemma, then we cannot say anything. Okay. So this is the point. If you satisfy pumping lemma, if a language satisfy pumping lemma, we cannot say anything. So finally, this is my question. Tell me the answer for this question. Pumping lemma, this statement, this theorem can be used to prove regularity? Never. We cannot use it to prove regularity, but we can use it to prove non-regularity. Yes or no? And when it will happen? We can use it to prove non-regularity, but when you don't satisfy pumping lemma. So remember, when L does not satisfy pumping lemma, this pumping lemma, then we can guarantee that L is non-regular. Then we can say L non-regular. Okay, so using pumping lemma, you can never do this conclusion. Is this point clear? Using pumping lemma, you can never come to this conclusion. But you can come to this conclusion. Okay, if language does not satisfy pumping lemma, then you can say L is non-regular. I hope all these points are clear. Okay, so very simple. Now let's move on. So far, did we study pumping lemma? So far, remember, so far we did not study what this pumping lemma says. Actually, so far what we are doing, this is your pumping lemma statement. This is the pumping lemma statement. We are not going inside this pumping lemma statement. We are just here. So far we are here. Yes or no? So far we are outside. In this outside market, we are there so far. Okay, so far we did not study what is this pumping lemma statement. Now what we will do? Now we need to study this. Now we need to go inside. Okay, now we study this statement. Now we need to see what is this statement. Now we need to study inside what is this statement. Okay, so now let's see. So the point is, now we are going to study what this pumping lemma says. Means this pumping lemma, what is this statement? That is what we will study now. Okay, this statement we are going to study now. Now let's start. Okay, so far everything is clear. Please tell me. Let me know. So far whatever we have seen, that is clear. Don't worry about other things. So far whatever we have seen, that is clear, right? Okay, very good. So chapter 1 is over. So far whatever you have seen, from that 5 questions are there in GATE, TIFR, ISRO exams. Let me tell you. Okay, let me tell you something very interesting. That so far whatever we have seen, all the questions are from that. So far what we have seen, I can say in the GATE exam, UGC NET exam, TIFR exam, almost 90% questions are from that. Okay, so remember, almost, or I can say more than 90% questions. More than 90% questions are from that. Questions. Okay, more than 90% questions in GATE exam plus TIFR exam plus UGC NET exam plus ISRO exam. So if you collect all these exams, then more than 90% questions are from whatever we have seen so far. So if you stop right now, Okay, if you stop right now, then most probably whatever question will come, you will be able to solve. So without learning pumping lemma, you can solve the questions of pumping lemma. Okay. Did you notice? Did you notice that without learning what is pumping lemma, without learning what this pumping lemma says, without looking at what this pumping lemma says, without looking at this statement, you can solve most of the questions. You can solve more than 90% questions you can solve. Okay. But the interesting part is this. Let me tell you, in interview, they will ask you this. Definitely. And there is one gate question on this. Now, definitely some students are thinking, yes, let's leave it. There is one gate question on this. Means based on this statement, whatever we will study now, based on that, there is one gate question. But definitely many interview questions. In the interview, they can ask you this pumping lemma. Because the interviewer knows that people don't study this pumping lemma. They just study what is outside of this pumping lemma. Okay. They will study, but they will not go inside the pumping lemma. Anyway, so let's start what is inside this pumping lemma. So let's see this chapter 2. What does pumping lemma say? Okay, so let's start. And let me tell you, this is very interesting topic. Is there anyone who has seen my answer on GATEOverflow website of pumping lemma? I have written on the GATEOverflow website. I have written many answers on pumping lemma. Have you seen on this GATEOverflow website? More than 20 answers I have written based on pumping lemma. The reason is this is very interesting topic. This is very interesting topic. Okay. So now let's study this very interesting topic that is what this pumping lemma says. Okay. So let's focus on this. Now let's move on. So let's see what this pumping lemma says. And this is a very interesting property for regular languages. See what this pumping lemma says. This pumping lemma, what it said, it says that if you are regular means if L is regular language, if L is regular language, you can take any regular language. If L is regular language, then what will happen? Then there is a magical number for L. See, if L is regular language, then every regular language has a magical number. Then L has a magical number. L has a magical number. L has a magical number. This magical number, let's call it P. This magical number, let's call it P. This magical number is called pumping length. This is called pumping length. Okay. So don't worry. This is called pumping length, but we will use this word magical number. So anyway, the point is this magical number is called pumping length. Now, if L is regular language, then L has a magical number. L has a magical number. Now, what will happen with this magical number? So this magical number, what will happen now? Such that means, remember, every regular language has a magical number. Tell me, different languages, will they have different magical number? Different regular languages. If you take different regular languages, will they have different magical numbers? Yes. Remember, every regular language has its own magical number. Okay. It's not like fixed. It's not like that this fixed number for every regular language. No. Every regular language has its own magical number. Now, what will happen with this magical number? Such that, okay, so there is some magical number. Remember, there is some magical number. This L has some magical number. At least one magical number. Such that what will happen? In this L, tell me one thing. If I give you some magical number, for example, if I give you number 5, okay, if I give you number 10, then in this L, what I can do? I can create two parts. In this language L, I can create two parts. Those strings whose length is greater than equal to those strings. Here you have those strings. Whose length is greater than equal to P. Okay. So these are the strings whose length is greater than equal to this magical number. The remaining strings we don't care. These are the strings whose length is less than P. Okay, we don't care about these strings. Is this point clear? So in this language L, those strings whose length is greater than equal to P, for these strings, they can be pumped. These strings can be pumped. Okay, these strings can be pumped. W can be pumped. This is your pumping lemma. That's it. Okay, but now we need to study what this means. Yes or no? W can be pumped. What this means? This is what we need to study. Yes or no? But other than this, is everything clear? Please tell me. Remember this point. If you take a regular language L, you can take any regular language L. This regular language, remember, this will have some magical number. This will have some, at least one magical number will be there. At least one magical number. Okay, so this will have some magical number P. Now, what will happen? For this magical number, what will happen? In this L, inside this L, okay, focus, inside this L, there will be those strings. There will be some strings whose length is less than P, and there will be some strings. There will be those strings whose length is greater than equal to P, right? Yes or no? Now, what pumping lemma says? Pumping lemma says that in this area, these strings, pumping lemma says that these strings, in this area, whatever string you take, in this area, whatever string, in this area, every W, in this area, every string can be pumped. Can be pumped. Now let's see what this can be pumped means. What this can be pumped, what this means. This means that, okay, let me tell you what this means. Can be pumped. This is what we need to see. Can be pumped. W can be pumped. What this means? So this means that, first of all, you tell me this W is this W. Can I say its length is greater than equal to P? Can I say? Can I say this W, its length is greater than equal to P? Yes, because we are only interested in these strings. Remember, we are only interested in these strings in this language. Okay, these strings we don't care. We don't care. These strings we don't care. We don't care about these strings. We don't care. But the point is, these strings whose length is greater than equal to P, these strings can be pumped. Okay, these strings can be pumped. So you can notice the length of W is greater than equal to P. The length can be anything. The length can be very big. Okay, for example, maybe P can be 5 and this length can be maybe 100. Okay, is this point clear? So this P can be 5 and this W, the length can be 100. Now, what this means, pumped? This means that within the first P symbols, see, these will be the first P symbols because the length is greater than equal to P, right? Yes or no? This W, this is your string W. This is your string W. Now, in this string W, this will be the initial, this will be the beginning area. These will be the initial P symbols. This will be the initial P symbols. Now, within the first P symbols, what this means, can be pumped. What this means that within the first P symbols, you can find some section you can find. You can find some section. Remember, some section you can find. Some section. Section means substring. You can find some non-empty section you can find. Some non-empty section you can find. Okay. Some non-empty substring you can find. Section means substring. So within the first P symbols, you can find some non-empty section you can find. Let's call this section Y. Okay, let's call this section Y. Let's call it Y. Now, some non-empty section you can find such that this Y can be repeated 0 or more number of times. Okay, some section you can find such that I can repeat this Y 0 or more number of times. 0 or more number of times, and the resulting string will belong to the language L. Will belong to the language L. So I can say such that this Y can be repeated. This Y can be repeated 0 or more number of times. 0 or more number of times. Or I can say that it can be repeated greater than or equal to 0 times. And resulting string will belong to L. And this resulting string belongs to L. This is what it means, can be pumped. This is what it means. So far, I know you are not understanding. Okay, I know that. But just stay with me. This will become very easy. Don't worry. But what this pumping lemma says, again, I'm repeating. Just one more time, I'm repeating. Okay. This P is an integer. Remember this magical number P. This magical number. When I say magical number P, then this, remember, this P, this is a natural number. This P is a natural number. Okay. When I say this P is a magical number, here this P is natural number. Like, for example, you cannot take 1.2, 1.3. Okay. Don't take 1.2, 1.3. Okay. This is a natural number. means this P, this is greater than or equal to 1. This is a natural number. This magical number is a natural number. This magical number is a positive integer. I can say this magical number is a positive integer. Some positive integer. Okay, now let's see what this pumping lemma says. Just let's look at this one more time. Let's look at this. So basically you have a regular language. You have a regular language L. For this regular language L, what will happen? What is the first step? Tell me the first step. What this pumping lemma says? Pumping lemma says that for any regular language L, there exists a magical number. Yes or no? There exists a magical number. There exists a magical number P. There exists a magical number P. I told you that this magical number is a positive integer. This magical number is greater than or equal to 1. This magical number is a positive integer. So for this regular language L, there exists a magical number such that whatever string you take, for every string W in this L, whose length is greater than or equal to P, whose length is greater than or equal to P. Okay, means for every string this will happen. For every string in this L whose length is greater than or equal to P, what will happen? What will happen? For every such string, what will happen? I can say W can be pumped. For every such string, I can say W can be pumped. W can be pumped. Now what this means? W can be pumped. What this means? This means that in this W, this is your W, this is the entire string W. In this W, within the first P symbols, let's assume these are the first P symbols. These are the first P symbols. Within the first P symbols, what will happen? Within the first P symbol, you can find some section, you can find some non-empty section, you can find some non-empty section, let's call it Y, some non-empty substring you can find. Is this point clear? So within the first P symbols, I can say within first P symbols, within first P symbols of W, we can find there exists some section. Okay, we can find some. There exists a non-empty substring. There exists a non-empty section. There exists a non-empty section Y, which can be repeated any number of times. Which can be repeated any number of times. This section Y can be repeated any number of times, repeated greater than or 0 times. Okay, and the important thing, what is that? The resulting string should belong to the language, and the resulting string belongs to the language. And the resulting string, the string that will be resulting, that resulting string belongs to the language. A string belongs to the language. Okay, the resulting string must belong to the language. So this is what pumping lemma says. This is the simple statement of pumping lemma. Don't worry, we will take a lot of examples we will take, but this is what pumping lemma says in simple words. In simple words, I can say that if L is a regular language, you can read this in simple words. If L is a regular language, then what will happen? Tell me what will happen. There is some magical number. There is some magical number. Okay, L has some magical number. There will be some magical number such that you take every string whose length is greater than or equal to this magical number. Okay, in that string, we can find some non-empty section Y, which you can repeat any number of times. You can repeat this any number of times. The resulting string belongs to L. This is what pumping lemma says. Okay, this is what pumping lemma says. So in this pumping lemma, what matters? Don't worry, we will take a lot of examples, but what matters? In this pumping lemma, what matters? In this pumping lemma, you have this language. Okay, for this language, there is this magical number. Just wait. Okay, just wait. Magical number. So there is this magical number P. This magical number P. Now remember one thing. Which strings matter to us? Which strings matter to us? Only these strings in L. Inside L, these strings whose length is greater than or equal to P. Only these strings matter. Yes or no? These strings whose length is greater than or equal to P. Only these strings matter. Only these strings we care. We care about only these strings. Only these strings we care about. Remember this point. Only these strings we care about. Inside this L, those strings whose length is greater than or equal to P, only these strings we care about. And these strings must be pumped. These strings must be pumped. Okay, is this point clear? These strings, only these strings we care, and these strings must be pumped. For these strings, what will happen? For these strings, okay, let's call them, for example, candidate string. Okay, for a moment, let's call them candidate string. Is this point clear? Let's call them candidate strings. Because only these strings matter to us. Yes or no? Only these strings matter to us. Let's call them candidate string. Now, what should happen for every candidate string? What should happen? For every candidate string, W. Remember, who is a candidate string? Just tell me one last time. Who is a candidate string? Candidate string belongs to L and its length is greater than or equal to P. Okay. Candidate string belongs to L and its length is greater than or equal to P. So for every candidate string, what will happen? For every such string, what will happen? It can be pumped. W can be pumped. W can be pumped. Okay. Now, what that means? That means in this W, again, just look at this again, because this is important. In this W, within the first P symbols in the beginning area, these are the first P symbols. Within the first P symbols, what will happen? Within the first P symbols, tell me what will happen within the first P symbols. Within the first P symbols, there will be some section. There will be some section. There will be some non-empty section. This is some non-empty section. There is some non-empty section which you can repeat any number of times. This is some non-empty section. This non-empty section you can repeat any number of times. You can repeat any number of times. This non-empty section you can repeat any number of times. And the resulting string will belong to the language. Okay. So in this, what you can do, see, this is your Y. This area, let's call it X. This area, let's call it X. This area, let's call it X. And this area, let's call it Z. Okay. And remember, this non-empty section is Y. This non-empty section which can be pumped. This non-empty section can be pumped. This is the pumped. This is what we pump. Okay. This non-empty section, this is pumped. So tell me what will happen. If you repeat this any number of times, this Y power N means this N can be greater than or equal to 0. This N can be greater than or equal to 0. Means you can repeat this Y any number of times. This N is greater than or equal to 0. This resulting string, this is the resulting string, yes or no? Agree or not? If I repeat this Y any number of times, then this will be the resulting string. This will be the resulting string, and this must belong to L. This resulting string must belong to L. Okay, now let's see examples. So far, whatever we have seen, did you understand? I know you did not. Okay, I already know that you did not understand. Okay, so now let's see some examples. Let's see. So anyway, this is just whatever we have seen. This is written by Harry Mayerson. So you can see what this means. See this. Any regular language has a magic number. Read this. This is a very nice statement. Any regular language has a magic number. Such that any long word in L. Okay, you take long word means longer than P. Okay, any long word in L has the following property. Means these are the strings. These are the candidate strings. They have this property. Among the first P symbols, you can find some non-empty segment. Among the first P symbols, you can find some non-empty segment which you can repeat any number of times. And the resulting string will belong to L. Okay, leaves X among its kind means belongs to L. The resulting string belongs to L. So this is a nice poem. You can check it out. The complete pumping lemma is within this poem. Okay, so you can see what this omission means. Tell me. Means this segment why you have this is non-empty segment why you have repetition or omission. Omission means Y power 0. Okay, means you just remove this Y. This is epsilon, so that will be same as XZ. Okay, so that is the point. And the resulting string belongs to L. This is your pumping lemma. This is the poem of pumping lemma. Now let's move on. Now let's take examples. With examples, this concept will become more clear. So let's take many examples. Let's start now. Example number 1. This is our example number 1. Alphabet is A, B. The language is set of all strings that start with A. Starting with A, these strings. Okay. Prove that this will satisfy pumping lemma. We need to prove that L will satisfy pumping lemma condition. The pumping lemma condition will be satisfied by this language. This language will satisfy pumping lemma condition. We need to prove it. Okay, is this clear? We need to prove it. This is what we need to do. So now you tell me, if we want to prove it, what will be the first step? Just tell me this point. You already know this is regular language, yes or no? You already know L is regular language. We have created DFA for this. For this language, we have created DFA starting with A. You already know this is regular language. So tell me, what is the first step? We already know L is regular. This we already know. We already know L is regular. Okay. Now, because we have DFA for this. So what is the first step when you apply the pumping lemma? So tell me, in pumping lemma, now I apply pumping lemma. This is your pumping lemma. In this pumping lemma, the first step is that this L has a magical number. That is the step number 1. Yes or no? Inside this pumping lemma, the first step is that L has a magical number. L has some magical number. Yes or no? L has at least one magical number. L has at least one magical number P. This is our first step. Then we will do something. Okay, so first we have to find this magical number. That is the first step. Step number 1, find the magical number. Okay, so tell me one thing. How to find this magical number? That is important, right? How to find, for this language, how to find the magical number? This language will not tell us. If you ask this language, what is that magical number? This language will not tell you. Okay, this language is not going to tell you. So how to do that? We have to find it. Okay, so let's find it. So let's do it ourselves. Now, let me tell you how to find this magical number. The answer is hit and trial. Okay, hit and trial. That is the answer. Now, let me tell you one thing. You will be thinking, sir, if we apply the hit and trial, then there are infinite number of natural numbers we have to check. If we apply hit and trial, then we have to check P equal to 1, P equal to 2, P equal to 3, P equal to 10, P equal to 100, P equal to 1000, P equal to 1 crore, 1 trillion, 1 billion. Yes or no? Yes or no? Tell me. Please tell me. Yes or no? So the point is, if you apply the hit and trial, then you will be thinking that we have to check a lot of numbers. Maybe, for example, just think about it. There is some magical number. Do we know what is that magical number? Tell me. Do we know what is that magical number? We don't know. Maybe for some language that magical number can be 100. For some language that magical number can be 2. For some language that magical number can be 1000. For some language that magical number can be 1 crore. Okay. Or as Amitabh Bachchan says, 7 crore. For some language, the magical number can be 7 crore. Okay. So the point is simple, that we have to find this magical number, and the idea is hit and trial. But this is what I want to tell you. Once you become expert in pumping lemma, okay, once we finish this pumping lemma, I promise you that you will be able to guess the magical number just by looking at the language. Is this clear? Once we finish this pumping lemma, by the end of pumping lemma, you will become expert just by looking at the language. You will be able to guess the magical number. So don't worry about the magical number right now. Is this point clear? Right now, do not worry about magical number. Some students are thinking, sir, how to find that magical number? I am saying don't worry. Let's see hit and trial. So tell me, does P equal to 4 work? Okay, let's check. Will it work? Will this magical number work? Will this work? Will this P equal to 4 work? Okay, so tell me, if I take P equal to 4, then what I need to do? Okay, so let's assume P equal to 4. Now what I need to do? Tell me. Assume this is P equal to 4. Now tell me what we need to do. We have already fixed P equal to 4. Then what pumping lemma says? What is the further step of pumping lemma? Tell me. In pumping lemma, what are the remaining things we need to do in pumping lemma? In pumping lemma, what we need to do? Now we need to check, remember, which strings matter to us. which strings matter to us? Tell me one thing. I am asking a simple question. I am asking very interesting question. I am asking. Assume p equal to 4. Then tell me which strings we care about. Which strings we care about? Which strings we care about means which are candidate strings. Which strings we care about? These are the candidate strings. So tell me which strings are candidate strings. Can you give me some candidate strings? For example, this is your language. Remember, your language is starting with A. This is your language. Your language is starting with A. So tell me, can I say, tell me, can I say start the language? Remember this point, the language is starting with A. This is your language starting with A. So tell me, is this a candidate string? Is this a candidate string? If you take p equal to 4, if you assume p equal to 4, if you assume this p equal to 4, is this a candidate string? 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 Which of them is a candidate string? Tell me. So tell me which strings are candidate strings? What is the answer? Is this candidate string? No, this is not a candidate string because its length is not greater than equal to 4. You can notice its length. If you notice its length is not greater than equal to 4. Next, is this candidate string? This is also not candidate string. Why? Because this does not belong to L. This does not belong to L. This string does not belong to L. This string is a candidate string. This string is a candidate string. Is this point clear? The candidate strings, what are those? These are the strings which belong to L and whose length is greater than equal to P. I hope this point is clear. And I'm assuming P equal to 4. This is what I'm assuming. I'm assuming P equal to 4. So here I can say these are the candidate strings. Please tell me, is this clear? Which string is candidate string? Is this clear? Which strings we care about? Is this clear? Okay. Now what we need to do? So I'm already assuming P equal to 4. Now what we need to do? For candidate strings. Okay. For candidate strings means for every string we need to check. For all W in this language whose length is greater than equal to 4. For all these strings, we need to check, can we pump them? Okay. For every such string, can we pump W? Can we pump W? This is what we need to check. Yes or no? We need to check this. So tell me one thing. Can we pump? Like, let me take this string A, B, 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 B. Is this candidate string? Tell me. First of all, you tell me, is this candidate string? Yes, this is a valid candidate. I can say this is valid string. Okay, this is a valid candidate string. I can say. Okay, you can say that this is a valid candidate string. Yes. So we need to check this. So let's check. Can you pump it? Can you pump it? So if you check that this can be pumped or not, what you will do? This is your W. Your W is A, B, 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 B. This is your W. This is your entire string W. What this pumping lemma says, tell me. In which area you will check the pumping part? In which area you will check the pumping part? The pumping part in which area? In the first 4 symbols. Because remember, our P is equal to 4. This is our P. We are checking this P equal to 4. So within this, these are the first 4 symbols. These are the first 4 symbols. Okay, in these 4 symbols, we need to find out which part we can pump. Okay, yes or no? We need, remember, tell me something interesting. Okay, so if I take this as Y, then if I repeat this Y 0 times, then what will happen? See, let's assume, see what I'm saying. Did you understand? I am saying that assume this is Y. Assume, okay, take, or I can say, take Y equal to A. take y equal to a. Okay, if I take y equal to a, tell me, will this y equal to a satisfy? Will this y equal to a satisfy? Will this y equal to a satisfy? Means, for example, if I repeat it 0 number of times, then what string I will get? Repeat y 0 number of times. Repeat y 0 times. Then what a string I will get? What string I will get? What is the resulting string? What is the resulting string? The resulting string is B, 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 B. Does it belong to L? This resulting string, does it belong to L? Does it belong to L? This does not belong to L. This does not belong to L. So can I say pumping lemma is not satisfied by this language? Can I say pumping lemma is not satisfied by this language? Can I say this string cannot be pumped? Okay, so can I say, so y equal to a does not work. Does not work. Y equal to a does not work. So can I say that string w, cannot be pumped? Can I say this cannot be pumped? Tell me. Can I say this cannot be pumped? Please tell me. Can I say this cannot be pumped? Can I say this cannot be pumped? The answer is no. If this does not work, try something else. Ultimately, we want some part. Yes or no? The answer is no. If remember this point, if y equal to a, if y equal to a, if this section does not work, try something else. If this section does not work, then try some other section. Then try some other y. Is this point clear? Try some other y. Yes or no? Ultimately, tell me what we want. Pumping lemma says that we want some section. Remember this point. Pumping lemma says that we want some section. Okay, we need some section. Some. We need some section. We need some section y which can be repeated. Okay, which can be repeated and resulting string belongs to L and results in L, which can be repeated and results inside L. Is this point clear? And the result is inside L. Is this point clear? Tell me. Remember, pumping lemma says that we want some section. I told you this point, if you remember. I told you that you have this W. This is your W. W length is greater than equal to P. Okay, and W belongs to L. I told you that within the first P symbols, these are the first P symbols. Okay, these are the first P symbols. Within the first P symbols, some part we need. Yes, agree or not? Please tell me. We just need some part. We just need some non-empty part we need. Some non-empty substring we need. Some non-empty section. Okay, some non-empty substring y we need. Okay, some. Focus on this word some. Please focus on this word some. This is very important. Okay. Please take care of some and all. In pumping lemma, take care of these words. These words are very important. These words, some word and all word. Some versus all. Is this point clear? So remember, very simple point that if you take this W, which is a candidate string, in this W, within the first P symbols, there is some part. There is at least one part. There is at least one part which you can repeat. So let's call this X and let's call this Z such that what should happen? Such that this Y you can repeat any number of times. And this resulting string, this is the resulting string. This resulting string belongs to L. Okay, so remember this point. If this does not work, if this Y does not work, then we will check some other Y. So give me suggestion, which Y will work? Tell me which Y will work. Which Y will work? Which y will work? Give me some suggestion. Which y will work? Can I take y equal to empty string? Can I take y equal to empty string? For example, can I take y itself as empty string? If I take y itself as empty string, if this empty string I take as y, if this empty string, if I take this as y, then definitely result will belong to L. Yes or no? If I take y equal to empty string, then definitely I can repeat this empty string any number of times. I can repeat this empty string any number of times. The result will definitely belong to L. Actually, the result will be this. So can I take y equal to empty string? This you can never do. Okay, don't do this. Don't do this. Don't do this, because that will be trivial. Do you agree with me? That it will be trivial. If you take y equal to epsilon, that will be a trivial thing. That will be a trivial thing in any string. For example, if you take this string a, b, b, and in this string, if you take y equal to empty string, let's assume you take this part, this empty string you take as y, then you can notice that, let's call it x and let's call it z. Your w is equal to a, b, b, b. Now you can easily notice, if I do x y power n z, then you can notice y power n, that is nothing but empty string power n, that is empty string. So that will be same as xz, that will be same as abb, and that will definitely belong to L. That will definitely belong to L. So y equal to empty string, this is nonsense. Yes or no? Y equal to empty string, that will always work. Y equal to empty string will always work. That becomes nonsense, or I can say trivial. That will always be pumped. That becomes trivial, or I can say nonsense. So don't take y equal to empty string. This is what I'm saying. I'm simply saying that don't take y equal to empty string. Yes, x can be empty, z can be empty, but y cannot be empty. Okay, we only care about y. We don't care about x comma z. We do not care about x comma z. We only care about y. The y cannot be empty. So you cannot, okay, never take this. So remember, never take y equal to empty. Okay, non-empty substring you need. So now tell me which y will work. So can I take y equal to bb? Will it work? If I take y equal to bb, will it work? Just tell me. Y equal to bb, will it work? Means if I take y equal to bb, if I consider this as y, if I consider this as y, then will it work? Now tell me, what is your x? If I consider this as y, then what will be your x? Then this will be your x, and this remaining will be your z. This remaining will be your z. Okay, so tell me now you tell me, if I repeat this y any number of times, will it belong to L? If I repeat this bb, if I repeat any number of times, will it belong to L? Yes, it will always happen for all n. For all n greater than equal to, okay, this will definitely happen. You can notice this will definitely happen. For example, in this a, b, 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 in this you can notice this is your w. This is your w within the first four symbols. These are the first four symbols. Because p equal to 4. So that is the reason first four symbols. Here we need non-empty part. This is your y. I am assuming this is your y. If this is your y, then automatically this left thing will become x and this right thing will become z. Now, if I repeat this y 0 number of times, what I will get? Repeat y 0 number of times. What I will get? Repeat y 0 times. What I will get? Tell me. Repeat y 0 times. If I repeat this y, if I repeat this bb 0 times repeating means bb gone. Yes or no? If I repeat this bb 0 times, then bb gone. So finally, a, b, 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 b. This also belongs to L. Can I say this belongs to L? Yes, of course. This starts with a. The language is starting with a. You know what is the language? Your language is starting with a. This is your language starting with a. Now you tell me, if I repeat this y one time, what I will get? If I repeat this y one time, what I will get? I will get this entire string. I will get this w itself. This w itself I will get. I will get this w itself if I repeat one time. And you can notice that also belongs to L. If I repeat this y 2 times, then what I will get? If I repeat this y 2 times, then then also that will belong to L. So finally you can notice, you can repeat this Y any number of times. This BB you can repeat any number of times, 100 times, 1000 times, 1 million times. The resulting string will belong to L. The resulting string that will definitely belong to L. Whatever value you of N you take, this you can repeat any number of times. The resulting string will belong to L. So now tell me. So final conclusion. What is the final conclusion? Can I say that this magical number works? So pumping lemma is satisfied or not? So pumping lemma is satisfied or not? So can I say pumping lemma satisfied? So can I say pumping lemma satisfied? Can I say pumping lemma satisfied? No. So can I say pumping lemma satisfied? No. You have to check for all strings. Every candidate string must be pumped. Every candidate string must be pumped. Please understand. So far only one string we have checked. So can I say, so I can see, so W equal to ABB, BB. Okay, see, this can be pumped. This can be pumped. This can be pumped. So can I say L satisfies pumping lemma? Can I say L satisfies pumping lemma? Can I say L satisfy pumping lemma? The answer is no. The answer is no, not yet. No, not yet. Yes or no? Not yet. Because we have to check every candidate string. Remember this point, that every candidate string must be pumped. We have to prove that every candidate string must be pumped. Every candidate string can be pumped. Can be pumped. Yes or no? Okay. Is this clear? Yes or no? We have to prove that every candidate string can be pumped, because pumping lemma says that every candidate string can be pumped. Agree or not? You know the pumping lemma. The pumping lemma says that every candidate string can be pumped. There exists a magical number. There exists a magical number such that every candidate string, whatever W you take, for every, remember this point, every candidate string, whatever W you take, this is your candidate string, whatever W you take, W's can be pumped. W can be pumped. Okay, this is your pumping lemma. So now you tell me one thing. Like this, if I keep checking the strings, then how many strings I need to check? Tell me. Like this, how many strings I need to check? Your language is already infinite. Your language is already infinite, and these are the candidate strings. Your candidate strings are infinite. Yes or no? So like this, will I keep checking every string one by one? Will I check every string one by one? Like this, will I check every string one by one? No. So I will tell you how to check. I will tell you how to check all the strings together. How to check all the strings together, I will tell you. But before that, for practice, you tell me how to pump this string. For example, this string, how to pump A. Is this valid string? First of all, you tell me, is this candidate string? Remember your P equal to 4. Your P equal to 4. So you can notice this belongs to L and its length is greater than equal to P. So this is candidate string. Its length is greater than equal to P. So remember, this is candidate string. This is a candidate string. Okay, so we have to check this. So now tell me, which Y will work? Can you pump it? Can we pump this string? Can we pump it? Tell me. Can we pump? Can I pump this string? This string can we pump? Which Y you will take? In this string, which Y you will take? This is your string. Within the, how many symbols you will check? Tell me, which area you will check? Within the first 4 symbols you will check. Yes or no? Within the first 4 symbols. Within the first 4 symbols you will check. So you will check within the first 4 symbols. Within first 4 symbols. Okay, within first 4 symbols. Tell me which Y will work. For this string, which Y is going to work? Which Y will work for this string? For this string, which Y works? So can you notice? Can I take this Y equal to A? Will it work? Can I take this Y equal to A? Can I take this Y equal to A? Will it work? Will it work? This Y equal to A, if I take, will it work? Just check it. Will this, so this will work or not? So here, what is your x? Tell me. If this is your y, take y equal to this. So tell me. If I take this y, then what is your x? Your x is empty. Okay. If I take this y, then I can say that your x will be empty. This x will be empty. So you can easily notice, if I take, okay, take y equal to a. If I take y equal to a, this a, then you can notice, x will be empty string. And what will be z? Z will be remaining string. Z will be the remaining string. Now you tell me, if I repeat this a any number of times, what will be the result? Means I repeat this a any number of times, this string, this will be the resulting string. Does it belong to L? Does it belong to L for every n? For every n, does it belong to L? If I take n equal to 0, what string will be the resulting string? If I take n equal to 0, which is the resulting string? That will be triple A. If I take n equal to 0, triple A, this will be the resulting string, and this belongs to L. If I take n equal to 10, I will get a power 13. That also belongs to L. So can I say this works? Can I say take y equal to a? This works or not? Yes, this works. Yes, it works. Yes, it works. Okay. But tell me one thing. Remember, we only need some y. But actually, this y will also work. Yes or no? Agree? Actually, this y will also work. If you take y equal to double A, that will also work. Okay, no one is stopping. So y equal to double A, that will also work. That also works. But we only care about one part. Agree with me? See, this will also work. If you take triple A, y equal to triple A, that will also work. If you take y equal to triple A, okay, remember, if you take y equal to triple A, if you take this as y, that also works. But we only care about some y. Okay, in every string, some part should be pumped. In every candidate string, at least one part should be pumped. At least one part you have to find which you can repeat. Is this point clear? In every candidate string, at least one part you have to find which you can repeat, such that resulting string will belong to L. Okay. So anyway, I can say that this string is also satisfied. So can I say that, so far we have checked how many strings? Tell me. So far we have checked 2 strings we have checked. But how to prove that all the strings, all the candidate strings will satisfy? Now let's see the general proof. Okay, now let's see the general proof. Now we will prove that every candidate string can be pumped. Okay, remember, now we will prove that every candidate string, every W, okay, now we will prove that every W which belongs to L and whose length is greater than equal to 4, every W can be pumped. Okay, so how to do this general proof? In this general proof, can I take a specific string? Please tell me. In the general proof, can I take a specific string? No, I cannot take a specific string. Now, how to do this? See, you know that whatever string you will take, whatever candidate string you will take, how it will look like? Whatever candidate string you will take, definitely it will look like this. Something here, something here, something here. Okay. And there can be like this. Okay. This is what your candidate string will look like this. Okay. Remember, your candidate string has length at least 4. This you already know. This is what your W will look like. Is this clear? Every candidate string looks like this. Okay. Every candidate string will look like this because every candidate string has length greater than equal to 4 and it belongs to L. Okay. Now you tell me. Okay. So now this is the general case I have taken. You can notice here the length of W is greater than equal to 4. You can notice the length is greater than equal to 4 and you can notice W belongs to L. Now you tell me which Y will work. First of all, in which area you will find the Y? In which area you will find the Y? You will find the Y within the first 4 symbols. Within the first 4 symbols, we will find the Y. Okay. So let's find the Y within the first 4 symbols. So within the first 4 symbols, these are the first 4 symbols. Okay. In these first 4 symbols, which Y will work? Tell me. Can anyone tell me which y will definitely work? Whatever string you take, which y will definitely work? See, I guarantee that, see, this y will definitely work. Okay, you can take, can I say this y will work? Can I say this y will work? Can I say this y will definitely work? No, 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 no. Can I say this y will definitely work? Can I say this y will definitely work? No, because maybe this is BBB. Okay, because maybe this is BBB. So if I take y equal to a, then there is a problem. If I take y equal to a and I repeat this 0 times, will the resulting string belong to L? If I take y equal to a, and if I repeat this 0 number of times, the resulting string, will it belong to L? No. So tell me which string will work. Then tell me which y will work. I guarantee that this second symbol, this y will definitely work. This y will definitely work. Agree? Do you agree with me that this y will definitely work? Okay, so you can easily notice this second symbol equal to y will definitely work. This y equal to second symbol, definitely works for every string. Definitely works for every string. This second symbol can be A, this second symbol can be B, I don't care. But this works for every candidate string. Okay, is this clear? Did you understand? So tell me, if I take this y equal to a, means this is the general case, this is your string. First, okay, then you have this, and then you have this. This is your W. This is the general case I am taking. Now in this, these are the first 4 symbols. If I take y equal to this symbol, if I take this y equal to this symbol, then can you notice? Then tell me, first of all, if I take y equal to second symbol, then what will be x? If I take y equal to second symbol, what will be x? X will be a, and what will be z? The z will be this remaining string. This remaining string will be the z. Okay, this remaining string will be the z. So very simple. This remaining string will be the z. Now you can notice this remaining string. Okay, so now you tell me, can you guarantee that this x, y power n, z, this will belong to L, whatever n you take, for all n greater than equal to 0? Can you guarantee? Can you guarantee that this will happen? Yes, this will definitely happen. This second symbol you can repeat any number of times and this will work. Okay, so that's it. Some part we need, right? See, some students are saying that x equal to this third symbol will also work. Is this correct? Some students are saying y equal to third symbol will also work. Is this correct? Can I say y equal to third symbol will work? Yes, y equal to third symbol will work. But do I care about that? I only care about some y. I only care about some section can be repeated. Within the first p symbols, some section can be repeated. Within the first p symbols, at least one section can be repeated. I agree with you that third symbol will also work. If you take third symbol, if you take y equal to third symbol, that will also work. I agree. If you take y equal to third symbol, that will also work. In this situation, x will be this. So remember, if you take y equal to third symbol, if you take this symbol equal to y, that will also work. I know. But the point is, we need some y which you can pump. Some y you can pump, and that's it. So definitely, now tell me, now can I say that we have proved the pumping lemma? Now can I say that this language will satisfy pumping lemma? Now what we have done, let me tell you. Now we have proven that, remember, now we have proven that this L satisfies pumping lemma. And what is your pumping length? You can see P equal to 4 works. This magical number works. And remember, do we need some magical number or every magical number? Do we need some magical number? Yes, some magical number. We only need some magical number. I only care about some magical number. This magical number works and I'm happy. And I can say pumping lemma is satisfied. Is this clear? See what we have done so far. Let me tell you. Okay, this is the summary. So this was our language For this language, what we did? For this language, we have proven. For this language, we have proven. What we have proven, let me tell you. Let me tell you what we have proven. We have proven that this magical number p equal to 4 works. We have proven that if you take p equal to 4, if I take p equal to 4, see what we have proven. We have proven that if p equal to 4 taken, if you take p equal to 4, then every candidate string can be pumped. Every candidate string can be pumped, And this is what pumping lemma says. Yes or no? And this is what pumping lemma says. So this is your pumping lemma. Yes or no? Agree or not? This is your pumping lemma. This is your pumping lemma. So I can say pumping lemma satisfied. So this language satisfies pumping lemma. And this I told you that every regular language satisfies pumping lemma. And you can notice this language satisfies pumping lemma. Yes or no? I told you every regular language satisfies pumping lemma. And you can notice this language satisfies pumping lemma. You can notice. All the small things I told you in this example, did you understand? All the small things I told you. Now let's see. If p equal to 4 works, then does p equal to 5 work? Will p equal to 5 work? Tell me. Tell me. You know p equal to 4 will work. For this same language, the language is same. For this same language, p equal to 4 works. How can you guarantee that if p equal to 4 works, then p equal to 5 will work? See, for this language L, this is your language L, a plus b whole star, this is your language L. Now, we know p equal to 4 works. This we have seen. We know p equal to 4 works. P equal to 4 works. How do you know this? Okay, first of all, p equal to 4 works, but how do you know this? Because we know p equal to 4 works. Why? Because the second symbol you can take as y. Okay, second symbol you can take as y. Agree? Because second symbol you can take as y. So you can see this p equal to 4 works because this second symbol can be taken as y. Okay, for all candidate strings. For all candidate strings, the second symbol can be taken as y. For all candidate strings. Okay, so very simple. Now this we have already seen that p equal to 4 will work. Now, how can you prove? We know p equal to 4 will work. Then can I say every p greater than equal to 4 will work? Can I say every p greater than equal to 4 will work? Every p greater than equal to 4 will also work. Will also work. Can I say every p greater than equal to 4 will also work? Yes, the same logic. Actually, the interesting thing is the answer is yes, and the logic will not change. The same y you can take. This is the interesting thing. The answer will be yes. If p equal to 4 is working, so every p greater than equal to 4 will also work. The answer is yes. And with the same logic, this is interesting. With the same logic, exactly same y, with the same y, it will work. Yes or no? You can notice p equal to 5 will work. Why? See, p equal to 5 will work. Why? Because you can notice that in p equal to 5, if you take p equal to 5, then your candidate string will be what? If p equal to 5 you take, now your candidate string will be what? Now your candidate string, what that will be? Now your candidate string will be w, whose length is greater than equal to 5. Whose length is greater than equal to 5. Now remember, now your candidate string is this. Now this is your candidate string. Agree with me? Do you agree with me that this is your candidate string now? Now your candidate string has length greater than equal to 5. Now tell me, which y will work? Can I say the same y will work which is working for p equal to 4? Which is working for p equal to 4? The same y will work. Yes, the same y will work. See, you don't even have to change the logic. The same y will work. This y will work. Okay, this y works. The same y will work. Is this clear? The candidate strings will change. Yes or no? If you take p equal to 5, the candidate strings will change. The candidate strings will change. Okay, your candidate strings, they will have length greater than equal to 5. But the point is the same y works. This is what I am saying. That same y will work. Is this point clear? Please tell me. Isn't it interesting that if p equal to n is working, then p equal to n plus 1 will also work. P equal to, so this is interesting point, and you can just simply see, you can just take this note that for any language L, for any language L, in pumping lemma, okay, remember, for any language L, whatever language L you take, for any language L, if p equal to t is working, or for example, if p equal to 10 is working, then which will also work? Then which number will also definitely work? Then p equal to 11, 12, 13, 14 also work. They will also work. Okay, so is this point clear? So I can say that if p equal to n is working, then every number greater than equal to n, that will work. Then n plus 1, n plus 2, n plus 3, and so on, they will also work. Is this clear? Please tell me. Is this understood? Let me know. Is this understood? This is very simple point. Is this understood? And what is the interesting point? They will also work, but what is the interesting point? The interesting point, with the same y, they will work. With the same y, they will work. Okay, with the same y as p equal to n. So they will work with the same y as p equal to n. With the same y, they will work. Okay, please tell me, is this clear? For example, in this previous language, a plus b whole star, in this previous language, can I guarantee that p equal to 7 works? Check it. Can I say p equal to 7 will work? First of all, if you check p equal to 7, then what will be your candidate strings? Tell me something. What will be your candidate strings? If you take p equal to 7, then your candidate strings will have length greater than equal to 7. Okay, your candidate strings, they will have length greater than equal to 7. Now you tell me one more thing. So this is your candidate string. This is the candidate string. It will have length greater than equal to 7. 4, 5, 6, 7. It will have length greater than equal to 7. This is your candidate string. Now tell me, within the first, how many symbols you will check? Where you will check y? Where you will find y? Within the first 7 symbols, you will find y. Okay, these are the first 7 symbols. In the first 7 symbols, you will find y. Can I guarantee that y equal to second symbol will work? Can I guarantee this y equal to second symbol will work? Yes, this will work. So can you notice the same y is working? This y equal to second symbol, this is working for p equal to 4. This is working for p equal to 5. This is working for p equal to 7. And this will work for any value of p greater than equal to 4. So that's it. So once p equal to n is working, will you check n plus 1, n plus 2, n plus 3? They will definitely work. I hope you understood. Are you finding this interesting now? Okay, slowly, are you understanding this pumping lemma and small points? Are you understanding? So for example, now something interesting. Tell me one thing. If p equal to 4 is working, then p equal to 5 will work, p equal to 6 will work. Why it is happening? For example, see, just logically you tell me, if p equal to 4 works, then why p equal to 5 is working? Then why p equal to 5 is working? Then why p equal to 5 works with the same y? Because remember, if p equal to 4 is working, then I'm asking why. See, I'm asking why with the same y p equal to 5 is working. The reason is simple. See. If p equal to 4 is working, that means y is where? Just tell me this point. That means y is where? Then y is within the first 4 symbols. Yes or no? If p equal to 4 is working, then y is where? Then y is within first four symbols. Within first four symbols, y you can find. Within first four symbols. Within first four symbols, this y you can find. This y you can find. Now tell me, if you increase this range, if you increase this p equal to 5, then also this same y will work, because this y you can find within the first 5 symbols also. Yes or no, agree or not? This y you can find within the first 5 symbols also. This same y you can find within the first 5 symbols also, within the first 6 symbols also, within the first 10 symbols also. Did you understand this logically? Think logically, think logically. If y is working, see, with the same y everything will work, because this y is present within the first 4 symbols. Within the first 4 symbols, this y is present. So if I take p equal to 5, then I can say that this y is present within the first 5 symbols also. This y is present within the first 10 symbol also. So p equal to 10 will also work. So p equal to 10 will also work. If I take p equal to 10, same y will work. Same y will work. No problem. The same y will work. Okay. So this is something interesting. Now tell me. Now you tell me one thing. If p equal to 4 is working, can I say p equal to 2 also will work? Can I reduce the range? Can I reduce the range? Can I reduce the range? No, that I cannot do. That I cannot do. So now I have to check p equal to 2 is working or not. Please check it. P equal to 2, will it work? Let's check p equal to 2 now. Okay, now our task is to check p equal to 2. So we are taking p equal to 2. What are the candidate strings? Tell me. Remember, your language is starting with A. Your language is starting with A. So tell me, if I take p equal to 2, then what are the candidate strings? If I take p equal to 2, what are the candidate strings? The candidate strings. What are the candidate strings? So I can say candidate strings are any string W which belongs to L and whose length is greater than equal to 2. These are the candidate strings. Okay. So tell me, can you pump? For example, this W equal to AB. Can you pump it? Can we pump it? Can we pump? Can we pump? Can we pump this? Let's check. Okay. So please tell me, for this AB, this is your AB. Within how many symbols you will check? Within how many symbols you will find y? Within how many symbols? Within the first 2 symbols, right? Within the first 2 symbols, because p equal to 2. So within first 2 symbols, find y. Within first 2 symbols. Within first 2 symbols, you will find y. Which y will work? Which y will work? Which y will work? See, this y will work. This y works. You can notice this y equal to this will work. Okay, if I take this equal to y, for example, if I take y equal to b, then what will be x? Then what will be x? Then x will be a, and what will be z? What will be z? Z is remaining string. Z is empty string. Okay, remaining string. Z is empty string. So now you tell me, can I guarantee that if I repeat this y any number of times, can I guarantee the resulting string will belong to L? Can I guarantee that if I repeat this y any number of times I repeat, the resulting string will belong to L? Yes. So I can say, can this be pumped? The answer is yes. Yes or no? We can pump it. This string we can pump. What about this string? W equal to AA. What about this string? Can you pump it? Can we pump? Can we pump this string? Again, the answer is yes. You can take, for example, for this string, what y you can take? For this string, you can take this y also. For this string, you can take this y also. No problem. Yes or no? This y will also work. For this string, this y will also work. Okay, this y will also work. Remember. For different strings, can you have different y? For different candidate strings, can you have different y? Can you have different y? Yes, you can have different y. Remember, for every candidate string, within the first p symbols, okay, some y you need. Different candidate strings can have different y. Please understand. different candidate strings can have different y, Okay. So for example, for this string, this y will also work. For example, this y also works. Remember, I can say this y also works. Okay, this y also works. So I can say, so tell me what is x now? If I take y equal to this first a, then what is x? Now x is an empty string. What is z? Z is a. Now z is a. Now z is a. Okay, now tell me. So can I guarantee that x, y power n, z, can I guarantee that will belong to L? Can I guarantee that will belong to L? If you repeat this y any number of times, okay, if you repeat this y any number of times, can I guarantee the resulting string will belong to L? Yes. So I can say this also works. This also works. So remember this point. If you notice this point, I want to tell you, remember, different candidate strings can have different y. Remember, different candidate strings can, for different candidate, I can say, remember, for different candidate strings, different y can work. Okay, is this clear? Different y can work. This is the note. For different candidate string, different y can work. Because remember what pumping lemma says. Don't forget what pumping lemma says. Okay, remember what pumping lemma says. Pumping lemma simply says that every string can be pumped. Now you can pump different strings in different way. Okay, this pumping lemma simply says that if L regular, then there exists a pumping length, then there exists a magical number p, then okay, there exists a magical number p such that every candidate string, every w you take, for all w which belong to L whose length is greater than or equal to p, okay, every w such that every w can be pumped. Okay, every such w can be pumped. But remember, different w can be pumped in different way. Yes or no? Every such w can be pumped, but different w can be pumped in different ways. Different w's can be pumped in different ways. Or same ways. In different ways or same ways, that does not matter. Ultimately, the only thing matters is, can you pump it? Yes or no? Agree or not? See, different w, they have different y, same y, we don't care. Yes or no? Different candidate strings, they have same y, different y, we don't care. Ultimately, every w, every candidate string should be pumped. Every such w should be pumped. You should be able to pump it. So different w's can be pumped in different ways. Means different w's can have different y. Okay, for different strings, for different candidate strings, different y can work. Okay, let's move on. So tell me, we have already checked for this p equal to 2, we have already checked a, b. So can I say that all the, did we check for all the strings? We have checked for ab, we have checked for a. Then can I say that for all candidate strings we have checked? No, we did not check for all candidate strings. So now the general result. We need to check for all candidate strings. So now you can see the general solution. Tell me what is the general solution. First of all, what the candidate string will look like. You tell me this point. Your candidate string, how that will look like. See, that will look like this, starting with A, and at least 2 symbols will be there. This is your candidate string. Very good. Okay, this is your candidate string. Now you tell me, within how many symbols you will find y? Within first 2 symbols. Okay, within first 2 symbols. Within first 2 symbols you will find y. Please tell me, can I guarantee that this y will definitely work for every string? Can I guarantee that this y will work for every string? This y will work for every string. Can I guarantee? One more thing you tell me. Can I say this y will work for every string? Can I say this y will work for every string? No. For example, if you take b here, then this y will not work. Yes or no? If you take the second symbol equal to b, now this y will not work. If you take, now remember, this y equal to a does not work now. Does not work. This y equal to a does not work when second symbol b, when second symbol is b. Yes or no? When second symbol is b, then y equal to a, this will not work. Tell me why it will not work. This second symbol, why it will not work? Because if you repeat it 0 times, the resulting string will not belong to L. If you repeat it 0 times, if you repeat 0 times, you remove it. If you repeat 0 times, then the resulting string, this is the resulting string. See, the resulting string will be this. This does not belong to L. Okay, so very simple. So remember, y equal to a, this does not work when second symbol is b. So tell me, I can simply say, in simple words, I can simply say that this y will always work. Okay, whatever string you take, I can say y equal to second symbol always works. Always works. Okay, yes or no? This y equal to second symbol, this always works. Because tell me, if I remove this second symbol, then resulting string, will it start with a? If I remove this second symbol, will it start with a? Yes, it is starting with a. If I repeat it 10 times, will it start with a? If I repeat the second symbol 10 times, the resulting string, will that start with a? Yes, that will start with a. So you can notice y equal to second symbol always works. So now I can say that p equal to 2 works. Yes or no? So we have seen that p equal to 2, this works. This works for L. P equal to 2 works for L. So finally, remember, for this language, how many p's are working? Tell me, so far we are only analyzing this language. For this language, how many p's are working? For this language, you can notice p equal to 2 is working. If p equal to 2 is working, can I guarantee p equal to 3 will work? Can I guarantee p equal to 3 will work? Yes, that will also work. So p equal to 3 will work. P equal to 4 will work. This we have checked also. If you remember, this we have verified. If you remember, this we have verified. This we have verified. Similarly, p equal to 5 will work. P equal to 10 will work. So I can say p greater than equal to 2 works. So for this language, how many magical numbers are there? For this language, how many magical numbers are there? For this language, how many magical numbers are there? Infinite number of magical numbers are there. Yes or no? For this language, infinite number of magical numbers you have. Is this understood? Now something finally interesting. This, for this same language, p equal to 1 will work or not? For this same language, p equal to 1 will work or not? For this same language. Why it is not working? I guarantee that p equal to 4 will not work. P equal to 1 will not work. For this language, this is your starting with a. For this language, if you take p equal to 1, why does it not work? Why does it not work? Which string you cannot pump? If you take p equal to 1, then tell me which string will violate. Tell me which string will violate. Which string will violate? Means which string will violate? Or I can say which string you cannot pump. Or I can say which string cannot be pumped. Which string cannot be pumped? Cannot be pumped. Cannot be pumped. So tell me, which string cannot be pumped? Some strings I am giving you. I am giving you some strings. Tell me one by one. Some strings I am giving you. Will this violate? Will this string violate? Will this string violate? Tell me which string will violate. If I take p equal to 1, if I take p equal to 1, which string will violate? Will it violate? Will it violate? Will it violate? Will it violate? And will it violate? Tell me, which string will work? First of all, you tell me, when you are checking p equal to 1, which strings will you check? Like, to which strings you will give some attention? To which string you will give attention? Only candidate strings. Okay, only candidate strings. First of all, when you take p equal to 1, then your candidate strings are what? Your candidate string, these are the strings that matter. These are the strings that matter. These are the strings that will matter. So your candidate strings belong to L and their length is greater than or equal to 1. These are the candidate strings. So first of all, I don't care about this string. Tell me, do I care about this string? Do I care about this string? No, because this string does not belong to L. So can this string violate pumping lemma? Can this string violate pumping lemma? No, I don't care about this string. I don't care about this string. Okay, इस स्ट्रिंग को कोई भाव भी नहीं दे रहे अपन. Okay, हम लोग इस स्ट्रिंग को कोई भाव नहीं दे रहे. So we don't care about this string. इसको कोई भाव नहीं देना है. ठीक है. Next, what about this second one? This second one. This string also we don't care. This string also we don't care because this does not have length greater than or equal to 1. This string, yes, this string can be pumped, right? See, this string you can pump. Which part you will take as y? Which you will take as y? You can take this as y. For example, this second symbol you can take as y. This second symbol you can take as y. So this can be pumped. Okay, remember, yes or no? So this string is actually pumped. This string is actually pumped. You can pump. This string you can actually pump. Next, what about this string? Can you pump? Yes, you can take this as y. So this string also can be pumped. What about this string? What about this string? Which part can you pump? In this string, which y you will take? In this string, which y you will take? In this string, which y you will take? No, this is not even a candidate string. This is not even a candidate string. इस string को कोई भाव नहीं देना है. We don't care about this string. We don't care about this string also. Now tell me, here you can pump this. This y equal to a. You can take this. So this you can pump. You can take this and this will be oh, sorry. Because p equal to 1, so y must be within the first one symbol. Sorry. See, p equal to 1. Okay, let me tell you. See, p equal to 1. So where you will find y? Tell me, where you will find y? This p equal to 1. So first of all, candidate strings. What are the candidate strings? Those are the strings which belong to L and their length is greater than or equal to 1. Tell me where you will find y. Where to find y? Where to find y? Tell me where to find y. Within the first p, within the first symbol, means only first symbol. Yes or no? Within first p symbol, and that means within first p symbol, within first one symbol, means only first symbol can be taken as y. Only first symbol can be taken as y. Yes or no? See, if you take p equal to 1, if you take p equal to 1, then only possibility for y, what is that? Then only possibility for y, what is that? Tell me. Then only possibility for y is first symbol. Is first symbol. Because remember, whatever string you take, in that string, within the first one symbol, we need y. We need y. Okay, within first one symbol, we need y. And only there is one symbol. There is only one symbol, so that must be y. There is only one symbol, so that must be y. This must be y. Yes or no? Agree or not? This must be y. So tell me, which strings again? Okay, which strings cannot be pumped? See, we don't care about this string. 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 Because these strings, they do not belong to L. These strings, they do not belong to L. We don't care about these strings. What about this string? What you can pump here? See, this y if I take, then can I pump it? Is it pumpable? Is it pumpable? If I take y equal to this, if I repeat it any number of times, the resulting string, will it belong to L? If I repeat this any number of times, the resulting string will belong to L, right? If I repeat this 0 number of times, what will be the resulting string? If I repeat this 0 number of times, the resulting string will be AB, and that belongs to L. So I can say this is pumpable. See, this is pumped. Yes or no? This option is pumped. What about this one? What about this one? See, this cannot be pumped. This is your answer. This is your answer. This cannot be pumped, because if you take this Y, will it work? Can you pump this string? Please tell me. Can you pump this string? This string, if I take Y equal to this, then can I pump it? Can I pump it? No. If I repeat it 0 number of times, the resulting string does not belong to L. So remember, this does not work. Okay. I can simply say that if you take Y equal to this, then remember this point, that this cannot be pumped. Cannot be pumped. You cannot pump it. The question is asking what cannot be pumped. So the answer will be option 4. What about option 6? Yes, option 6 can be pumped. You can take Y equal to this. So option 6 can be pumped. This option 6 you can pump. What about option 7? What about this? This cannot be pumped. This cannot be pumped. So this also will be your answer. Your answer will be this also. So for this question, answer will be option 4, answer will be option 4, 7. Okay, answer will be option 4, 7. These will be the answer. For this question, answer will be option 4, 7. Please tell me, did you understand? So for previous question, what is the answer? The answer is string 4, 7. These strings cannot be pumped. These are the candidate strings which cannot be pumped. Which cannot be pumped. These are the candidate strings which cannot be pumped. Okay, so is this point clear? Tell me. Please let me know. Is this point clear? So finally, I can say P equal to 1 does not work. Okay, remember P equal to 1 for this language. Your language is this. For this language, if you take P equal to 1, then this will not work. Not work. Why this will not work? Because what is the violating string? Tell me which will be the violating string. Because violating string. Give me a violating string. For example, you can take this violating string A, or you can take this violating string AB. Okay, these are the violating strings. You can notice. Or you can take A double B, or you can take A double B. So that is also violating string. Tell me why this is violating string. For example, this W equal to A, why this violates? This is your W equal to A. This is your W. Within the first P symbols, here you will find Y. Within first one symbol, you will find Y. Okay, you will find Y. Here, within the first P symbol, you will find Y. So Y will be A. So if I take Y equal to A, so this will be Y. In this situation, if I repeat this 0 times, then what I will get? Tell me. Tell me. If I repeat this Y 0 times, repeat Y 0 times, what is the result? If I repeat this Y 0 times, then I will get this. And you cannot, this does not belong to L. This does not belong to L. This string does not belong to L. So I can say this Y does not work. So I can say, remember, so I can say that basically this string cannot be pumped. This string cannot be pumped. We cannot pump it. So Y equal to 1 does not work. Y equal to 1 does not work. So this is your language. We have done the complete analysis of this language. Actually, in this language, we have seen everything related to pumping lemma. I hope you understood so far. Don't worry, we will take more examples. But so far, did you understand that for this language, which are the magical numbers? So first of all, this language satisfies pumping lemma. We have proven it. This satisfies pumping lemma statement. This satisfies pumping lemma statement. Okay, we have proven it. Satisfies pumping lemma statement. We have proved it. Okay, and also P equal to greater than equal to 2, that works. So what is the minimum pumping length? What is the minimum pumping length? This is magical number, right? This magical number is called pumping length. I told you. This is magical number. This magical number is also called pumping length. This is also called pumping length. Okay, this is also called pumping length. So for this language, what is the minimum pumping length? If I ask you for this language, the minimum pumping length, the minimum magical number, the minimum pumping length, that will be equal to 2. That will be 2. So minimum pumping length will be 2. Okay, if 2 is working, then every number greater than equal to 2 will work. Every number, so p greater than equal to 2 also work. So p greater than equal to 2 works for L. Okay, p greater than equal to 2, that works for L. So this is your language. I hope you understood so far. Don't worry, let's take example 2. Can you take your copy pen? Can you take your copy pen for example number 2? Your language is ending with A. Now your language is ending with a string that ends with A. Okay, we have to prove that this language will satisfy pumping lemma. We have to prove it, that this language will satisfy pumping lemma. What is the first step? If you want to prove, you already know L is regular. We already know L is regular. This we already know. We already know L is regular. Yes or no? L is regular. So tell me, what is your first step in the pumping lemma? In the pumping lemma statement, what is the first step? The first step is find the magical number. Yes or no? Find the magical number. But the language will not tell you. Yes or no? The language will not tell you the magical number. We need to find the magical number, but the language will not tell you that magical number. What is that magical number? Language will not tell you. So what we need to do? We need to find it ourselves. Okay. So what is the method? The method is hit and trial. But I told you, once you become expert of pumping lemma, it will become easy for you to guess. It will become easy for you to guess. Now tell me one thing. Before the first example, it was slightly confusing what pumping length you should check, what magical number you should check, right? Before the first example. But now some idea you are getting which magical number you will check. Hit and trial. See, we are checking by hit and trial. We will check by hit and trial. But are you getting the idea which number should I start? By looking at the language. Your language is ending with A. Your language is ending with A. So tell me, from where should we start? Give me some rough idea. Give me some rough idea. From where should we start? P equal to 2. Okay, let's start with P equal to 2. No problem. Okay, so let me start. So hit and trial. But I told you one thing. Once you become expert of pumping lemma, you can guess this magical number. You can guess this magical number. Okay, so let's see. Okay, let's start with P equal to 3. Will it work? Let's start with P equal to 3. Will it work? Tell me. Will P equal to 3 work? Let's check. Directly give me the general solution. Does it work? If I take P equal to 3, first of all, your language is what? Your language is ending with A. Your language is ending with A. Okay. So this is your language. Your language is ending with A. Now you tell me, if I take P equal to 3, what are the valid strings? What are the candidate strings or valid strings? Candidate strings or valid strings to check. What are the valid strings? Means candidate strings means what are the valid strings to check? Valid strings that matter. Which strings will matter to us? Tell me. So you can easily notice that this string will matter. These strings which belong to L and their length is greater than equal to 3. These strings matter. These strings we need to check. We need to check. All these strings we need to check. Okay, now you tell me, if I need to check all these strings, I need to check all these strings and I am taking P equal to 3. Okay, one by one you tell me, I am giving you some strings and you tell me what is their Y. For example, okay, for example, if I give you this string, A, B, A, what is the Y? Is this valid string? Is this valid string? Which Y works? Which Y will work? Tell me, for this string, which Y will work? Just tell me. Yes, this is a valid string. For this string, which Y will work? First of all, where you will find Y? Okay, can I say this Y will work? Can I say? Okay, I'm asking which Y works. which y works for this string, for AAA, BA. Okay, which y will work for this string? So you tell me, will this work? Will this y work? Will this y work? No, 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 no. Remember, your y should be within the first three symbols. Okay, so no. Okay, this is an invalid y. This is invalid y because y should be within the first three symbols. Okay, because y must be in first three symbols. Okay, y must be here. In this area, y must be there. In this area. Is this point clear? So remember, this is my question. Will this y work? For example, my question is, will this y work? Does it work? This y works. This y, does it work? And the answer is no. Your y must be within the first three symbols. Okay. So this is invalid y. This is invalid y because y must be in the first three symbols. Means your y must be here. Here you must have y. Must have y. Okay. So now tell me. So which string, which will work? So I can say here. Okay. Here I can say that this y will work. For example, I can take y equal to this. This y will work. Yes or no? This y will definitely works. Okay, very simple. Is this clear? Please tell me. Yes or no? Let me know. Okay, so one y we need. Tell me how many y you need. Means tell me how many y you need. Only one y we need. In any candidate string, within the first p symbol, there should be some y. At least one y you need. If you have at least one y, be happy. Don't worry about other y. If you have at least one y, if you find at least one y which is working, then be happy. Don't worry about other y. Okay, there can be more than one y. Okay, one is enough. We only need at least one y. At least one y should work. At least one y must work. So this y is working. So be happy. So be happy. Okay, what about this string? If I take, for example, if I give you this string, first of all, is this a valid string? Is this a valid string? Tell me, is this a valid string? Tell me, this string. Yes, this is a valid string. Which y will work for this string? In the first three symbols, y must be there. So I can say this y will work. This y is working. Yes or no? You can notice. You can repeat this y any number of times. You can notice. First of all, if I take this y, then this will be what? Then this will be x. This will be z. Can you notice? X, y power n, z. You can repeat this y any number of times. Can you notice the resulting string will belong to L? Whatever repetition you do, you can repeat any number of times, 0 or more number of times, the resulting string will belong to L. Okay, is this clear? So tell me, now you give me the general solution. Now you give me the general solution. What is the general solution? First of all, your candidate string, how it will look like? When you have p equal to 3, then your candidate string, how it will look like? It will have at least three symbols. Yes or no? So it will have this symbol. There will be a first symbol. There will be a second symbol. Then there will be some symbols, but there will be a last symbol A. This is how your string will look like. Yes or no? Agree? This is how your string will look like. There will be a first symbol. There will be a second symbol. And there will be a last symbol. Okay, here you can have anything. This can be empty also. This can be empty also. This is how your string will look like. Now tell me which y will work for every string. You will find this y within the first three symbols. Okay, within the first three symbols you will find y. Yes or no? Yes or no? Within the first three symbols actually. For example, if this is empty, then the first three symbols will be this. Understand my point? If this is empty, if this part is empty, then first three symbols will be this. Okay, so the point is you will find the y within the first three symbols. So tell me which y will work. I can guarantee that second symbol equal to y will definitely work. This y equal to second symbol will definitely work. Yes or no? This second symbol, y equal to second symbol, will definitely work. I can say y equal to second symbol works for all w, for all candidate strings w. Yes or no? Y equal to second symbol, that will always work. That will always work for every candidate string. So can I say p equal to 3 is working? Yes, that's it. Yes or no? So p equal to 3 works. If p equal to 3 is working, then what can I say? If p equal to 3 is working, what can I say? P equal to 4 will also work. P equal to 5 will also work. P equal to 10 will also work. Okay, any p greater than equal to 3, that will work. Okay, yes or no? Now someone is asking, first symbol why not work? Did I say first symbol will not work? Tell me here, second symbol y equal to work. Second symbol will work. Did I say first symbol will not work? Did I say? Tell me, did I say first symbol will not work? Did I say? No, first symbol will also work, but I only care about some y. Yes or no? As soon as I will get at least one y, I am happy. I don't care about other y. I know second symbol will work. Now I don't care about first symbol. Yes, first symbol will also work. You can take first symbol equal to y. That will also work. Please understand. This y equal to first symbol will also work. This y equal to first symbol, that will also work. That will also work. But I need only one symbol. See, I need only one y. Is this clear to everyone? Please tell me. So as soon as you get some y which is working, if you are getting some y which is working, will you care about other y? Will you care about other possible y? No. We only need at least one y. In every candidate string within the first p symbols, at least one y we need, which we can repeat any number of times, and the resulting string belongs to the language L. So this is the point. Now let's move on. So tell me one more. Will p equal to 4 work? Yes, of course. Because p equal to 3 is working. So actually p greater than equal to 3 will work. Will work. These magical numbers will work. Now tell me, p equal to 2, will it work? Will p equal to 2 work? Will it work? Yes, this will also work. What y you will take? If you take p equal to 2, then what is the general solution? Just tell me directly the general solution. Now you are expert. Now you are expert of pumping lemma. Now you are expert of pumping lemma. Just take first symbol as y. Okay. Just take first symbol equal to y. Just take first symbol equal to y. Yes or no? Is this clear? This is the general solution. Just take first symbol equal to y in every candidate string. In every candidate string. Isn't it? Please tell me. Can you visualize? Can you visualize? Just take first symbol equal to y. Okay. So whatever string you have, whatever candidate string you have, in every candidate string, just take this equal to y. Whatever candidate string you have, I can give you any candidate string. I can give you any candidate string. In every candidate string, just take this symbol equal to y. Please tell me, if you do this, then can I say x, y power n, z, that will definitely belong to L? If you do this, can I say, if you repeat this first symbol any number of times, this first symbol, if you repeat any number of times, 0 or more number of times, can I say resulting string will belong to L? Resulting string will belong to L, yes, because resulting string will end with A. Because resulting string will end with A. So resulting string will belong to L. So I can say p equal to 2 is also working. Okay, so p equal to 2 is working. What about p equal to 1? Will it work? P equal to 1, will it work? This will not work. This will not work. For p equal to 1, who is the violating string? Who is the violating string? Please tell me, who is the violating string? This is the violating string. This is the violating string. Yes or no? This string is the violating string. Why this is the violating string? See, this string is the violating string because in the first one symbol you will find y. Where you will find y? within first one symbol, you will find y. Okay, and remember y is non-empty, right? I told you y is always non-empty. You know y is always non-empty. So tell me, what will be the only possibility for y? What is the only possibility for y? Y will be this. Now, if I repeat this y, zero number of times, what I will get? Remember, x is empty string, z is empty string. So if I repeat this y zero number of times, I will get empty string. That does not belong to L. That is not in the language, right? That is not in the language. So I can say this string cannot be pumped. So A cannot be pumped. I cannot pump it. So A cannot be pumped. So remember, for this P equal to 1, this string is the violating string. This string is the violating string. Yes or no? Is there any other violating string? Is there any other violating string? There is no other violating string. Okay, no other violating string. This is the violating string. No other string is violating string. No other string violates. No other string violates. Yes or no? Because in every other string, what you will do? In every other string, just take y equal to first symbol. In every other string, take y equal to first symbol. Take y equal to first symbol. That will work. So no other string is violating. But one string violates, that is enough. Yes or no? Yes or no? One string violates, that is enough. This string violates, that is enough. That is enough. So I can say y equal to 1 does not work. So tell me, this language, does it satisfy pumping lemma? This language ending with A, this language, does it satisfy pumping lemma? Does it satisfy pumping lemma condition? Does it satisfy pumping lemma condition? Yes. This satisfies pumping lemma condition. We have proved it. We have proved it. Okay. And tell me, what magical number will work? P greater than equal to 2 works. Remember this P. What this P is called? This P, this is magical number, but this is called pumping length. This magical number is called pumping length. So tell me, what is the minimum pumping length? Tell me the minimum pumping length. Minimum P. Minimum pumping length, that will be 2 for this language. Okay, slowly you will become expert of pumping lemma. I promise you. Once you understand pumping lemma, that will become very interesting topic. This is my promise to you. You will never feel bored in pumping lemma. If you solve 100 questions of pumping lemma, the next question, you will not feel bored. Every question is interesting because every question has analysis. Yes or no? Did you notice? In every question, basically, we have to apply some. It's not like there is a systematic procedure. We have to hit and trial. We have to check. First of all, we have to take P. Hit and trial, we have to take a pumping length. Some magical number we will check. For example, if we are checking P equal to 4. Now, when we are checking P equal to 4, now we have to find Y. Yes or no? Can you notice in this pumping lemma, every time we have to find some. First, we have to find some P. Then we have to find some Y. Okay, so like that. So this pumping lemma, this is a chapter of analysis. So this you will never feel bored in this chapter. So let's take example 3. Let's take next example. So tell me, this is your language A B star. Prove that it satisfies pumping lemma. Do you know this is regular? Do you know this is regular? A B star. Yes, we already know this is regular. You can create a DFA. We already know L is regular. This we already know. We already know L is regular. Why L is regular? You can create DFA for this. Okay, for this you can create DFA. You can create DFA, NFA, whatever. You can create DFA, you can create NFA, and this itself is regular expression. This itself is regular expression, yes or no? This itself is a regular expression. Is a regular expression. This itself is regular expression. Okay, so now you tell me, we need to prove that it will satisfy pumping lemma. We need to prove that it will satisfy pumping lemma. Do you remember I made you one promise? I made you one promise that slowly you will be able to guess what is the pumping length to check, which P to check. I told you. Do you remember? I told you, you will be able to guess. So tell me which P we should check. Which P should we check? Will P equal to 3 work? Will P equal to 3 work? Just tell me. P equal to 3. Let's check. P equal to 3. Does it work? See, this will not work. What is the violating string? This will not work. What is the violating string? Tell me. Violating string. Tell me the violating string. This triple A is the violating string. You can take this triple A. This is the violating string. Yes or no? This is the violating string. Actually, one more interesting thing. Actually, this is also violating string. This is also violating string. This is also violating string. Can you notice every string is violating string? Actually, every string is violating string. Every string violates. Every string of L. Every string belonging to L violates. Can you tell me why? Can you tell me why? See, these are the violating strings. Every string will violate. Why? Because notice, if I take P equal to 3, I am taking P equal to 3. Okay. Now you can notice this string will also violate. For example, this string. Take this string. Take this string. This string you take, it will violate. Why it will violate? First of all, where you will find Y? Tell me. In which area you will find Y? You have P equal to 3. So your Y must be within the first 3 symbols. Within first 3 symbols. Okay. Within first 3 symbols. In this area you will find Y. Okay. Yes or no? So here you will find Y. Now tell me, everything is A. Now whatever Y you take, if I repeat 0 times, just think about it. Here, whatever Y you take, whatever Y you take, if you repeat 0 times, what will happen? Tell me. Whatever Y you take, if you repeat that 0 times, what will happen? See, in this is your string A, B. Now, in this area, you take Y. In this area, whatever Y you take, whatever Y we take in this area, remember in this area, whatever Y we take, please tell me, whatever Y we take, for example, if I take Y equal to double A, whatever Y we take and we repeat Y how many times? We repeat Y 0 times. Then there is a guarantee that resulting string will have less than 3A. Yes or no? There is a guarantee. If we repeat this, whatever Y you take, you repeat that Y 0 times, then there is a guarantee. There is a guarantee that resulting string will have less than 3Y. Yes or no? Then resulting string will have less than 3A. Less than 3 A's. If you have less than 3 A's, will it belong to the language? Your language is this. Your language is this. If you have less than 3A, will it belong to the language? So can you notice no Y will work? Because whatever Y you take, for example, if I take this Y and I repeat 0 times, which is the resulting string? If I take this Y, I take this as Y and I repeat it 0 times, the resulting string will be BB. The resulting string will be BB. If I take this Y, the resulting string will be what? If I repeat this Y 0 times, I take this Y, I repeat it 0 times, the resulting string will be ABB. So did you notice whatever Y I take? This is very important. See, whatever Y you take, you can take this Y, you can take this Y, you can take this Y, you can take whatever Y you take. If you repeat that Y 0 times, then the resulting string will have less than 3 A's. Okay, the less than 3 A's. So the resulting string does not. So can I say this will not be pumped? So I can say this string cannot be pumped. Yes or no? This string cannot be pumped. Please tell me, did you understand? Please tell me, did you understand? Let me know. So remember, whatever Y you take, any Y you take, whatever Y you take, that does not work. So can I say this is a violating string? So I can say for this language, if you take p equal to 3, if you take p equal to 3, then what are the violating strings? Now can you tell me what are the violating strings? Violating strings are, these are the violating strings. This will be violating string. This will be violating string. This will be this will be violating string. Actually, every string will be violating string. Yes or no? If you take p equal to 3, then every w belonging to L violates. Every w belonging to L will violate. Okay. So can I say p equal to 3 will not work? So I can say this p equal to 3, that definitely not work. Okay. Yes or no? Interesting. Understood? Because in these strings, within the first 3 symbols, you will find y. See, whatever string you take, okay, see, whatever string you take, a, then whatever string you take, if you take p equal to 3, then within the first within the first 3 symbols, here you will find y. Here you will find y. Now tell me, whatever y you take, what will happen? Whatever y you take, what will happen? Whatever y you take, repeat 0 times. What will happen? Repeat 0 times. What will happen? The resulting string will have less than 3a. Yes or no? The resulting string will not belong to L. The resulting string will have less than 3a. Because if you take this, then they will be gone. If you repeat them 0 times. If you take this as y and you repeat 0 times, then they will be gone. Now you can notice you only have 1a. You only have 1a. Because these are b's. You know that these are b's. So I hope this point is clear. So tell me, will p equal to 4 work? So p equal to 3 is not working for this language. Will p equal to 4 work? Yes, that will work. See, p equal to 4 will work. Why? If you take p equal to 4, give me the general solution. Directly give me the general solution. If you take p equal to 4, then you can notice this will work. Because your strings are like this. Can you notice your string will be like this? And these are b's. Okay, your string will be like this. So which y will work? Your strings will be like this. Your strings, they will be like this. And where you will find y? Here you have to find y. You have to find y here. Okay, within first 4 symbols. Within first 4 symbols. Within first 4 symbols, find y. Within first 4 symbols, you have to find y. So tell me which y will work? Can you notice? This y will work. This y works. Isn't it? Yes or no? This y will work. So remember, if you take this, if you take any string whose length is greater than or equal to 4, whose length is greater, remember these are b's. These are b's. And you are checking p equal to 4. You are checking p equal to 4. So in this area, you can take this as y. Then what will be x? Take y equal to b. Then x will be what? Then x will be AAA. And then z will be what? Z will be remaining string. Whatever is remaining, z will be remaining string. So can you notice? Can I repeat this y any number of times? If I repeat this y any number of times, is there a guarantee that the result will belong to L? Is there a guarantee the result will belong to L? Yes. For all n greater than or equal to 0. You can repeat any number of times. This you can repeat any number of times. This symbol you can repeat any number of times. The resulting string will belong to L. There is a guarantee. So I can say p equal to 4 is working. If p equal to 4 is working, then p equal to 5 will also work. Yes or no? So p equal to 4 is working. It works. So p equal to 5 will also work. that will also work. So that's it. So for this language, we have proved pumping lemma. So this satisfies pumping lemma. This satisfies pumping lemma. Okay, this we have shown, this we have proved, and you can notice which magical number will work. These magical numbers will work. What is the minimum pumping length? What is the minimum pumping length? What is the minimum pumping length? That will be 4. That will be 4. Yes or no? Piyush is saying that if you take this string A, B, in this string, if I take P equal to 4, for P equal to 4, if I take this equal to Y and I repeat 0 times, what will be the, if I repeat 0 times, what will be the resulting string? Repeat this 0 times. What will be the resulting string? The resulting string will be this. Does it belong to L? Yes, it belongs to L. Yes, it belongs to L because your language is AAA B star. Your language is AAA B star. So your language is like this: AAA, AAA B, AAA double B, AAA triple B. Your language is like this. Is this understood? Piyush, is this understood? So yes, this is working. See, this Y will always work. You can take this Y. This fourth symbol you can take as Y. That will definitely work. Okay. So far, now are you comfortable with pumping lemma? So many examples we have taken. Are you comfortable with pumping lemma so far? Please tell me. Are you understanding pumping lemma? Pumping lemma is quite interesting. This is not, see, people don't study this nicely. That is the reason students, they think that this is very complicated. But if you study this nicely, if you understand this, okay, in a clear way, in a clear, correct, and complete way. So if you understand this clearly, then this is very, very nice topic. This is not so complicated, right? Actually, this is interesting. And can you tell me one more thing? Now, are you getting this experience that whenever I give you some language, immediately you can tell me, sir, this pumping length we can check. The magical number. Can you tell me like, sir, we can start with this magical number? Yes or no? Some idea you are getting, right? So once you look at the language, some idea you can get, some idea you can get some idea that, yeah, this pumping length we can try. We can check this magical number. We can check P equal to 4. We can check P equal to 5. If P equal to 5 does not work, then what should I do? If P equal to 5 does not work, then P equal to 6, P equal to 7. You can check like that. Yes or no? So we have just started pumping lemma. Let me tell you one thing. From pumping lemma, in the GATE exam, there is only one question which needs the statement of pumping lemma. Again, I'm telling you, in the GATE exam, in the last 40 years, there is only one question which needs the statement of pumping lemma. This statement of pumping lemma, this analysis of pumping lemma, there is only one question which needs. But that question came in 2019. That question came in 2019. So that is a recent question. So there is a chance that that type of questions can come in future. So don't skip pumping lemma. This pumping lemma we will teach in a complete way. I will teach. Okay, the complete pumping lemma I will teach. It will become long. I'm not saying, see, it will take maybe 6 to 8 hours. It will become. But I can promise you one thing. If you study this pumping lemma, whatever I teach you for next 5 to 6 hours, whatever I teach you, I promise you one thing, that in future, in GATE exam, whatever question comes, you will be able to solve. And I can also promise you that majority of the students will not be able to solve. So that is the benefit you are getting from pumping lemma, that you will be getting those 2 marks, and majority of the students, they will not get those 2 marks. Okay. So basically you are getting the benefit. See, in the GATE exam, if they ask you some scheduling question, in operating system, there is scheduling, right? If they ask you some scheduling question, will you get top rank because of scheduling? Because of scheduling question, can you get top rank? No, because every student will solve scheduling question. Every student, the student who is not preparing good, the student who is rote learning, they will also solve scheduling question. The student who is preparing very nicely, they will also solve the scheduling question. But you can notice, so because of scheduling question, you cannot get a top rank. You will get top rank if you solve the question of pumping lemma, decidability, synchronization, deadlock, Okay, transaction management, SQL. So these type of topics, if you solve the questions from these type of topics, then you will become topper, then you will get a top rank. So this pumping lemma is one of those topics. Okay, so far if you understood pumping lemma, then I promise you in future also you will understand, because the most complicated part of pumping lemma is gone. This lecture, this part 1, this lecture, this was the most complicated part of pumping lemma. If you are comfortable right now, then I can promise you in future you will be comfortable. Okay, so let's start the next session. So should we start the next session after half an hour, or please tell me, like, should we take the session tomorrow or should we start after half an hour? So we can start tomorrow. Okay, no problem, we can start tomorrow. Tomorrow you have operating system class also. After operating system class, I will take pumping lemma part 2. This pumping lemma we will study in multiple parts. This was part 1, this lecture was part 1. Tomorrow we will see part 2, then part 3, part 4. So in multiple parts we will see pumping lemma. But one thing I can promise you, that once the pumping lemma will be over, you will become expert of pumping lemma. And let me tell you one more thing. In future, you will never prove any language non-regular by some dumb methods. See, many students, what they do, some language is given, and if they want to prove that it is non-regular, then this type of logic they will use. It has one comparison, it has two comparison, it has matching, it needs to remember. This type of dumb logic they will use. Agree with me? Do you agree with me that most of the students, they will use this type of dumb logic to say that a language is non-regular? Okay, but once we finish this pumping lemma, you will be able to prove that you will be able to prove which languages are non-regular. Okay, that is the interesting part of pumping lemma. So anyway, so let's start tomorrow. Tomorrow we will study part 2 of pumping lemma. You can practice this part 1. Anyone has any doubt right now? Anyone has any doubt, you can ask. Okay, don't keep any doubt, just tell me what is your doubt. See, Sanjeev is asking, why are we not caring about strings of length less than p? Sanjeev, that we will see in the proof. Is this clear? In the proof we will see that. Okay, so just wait. Once we study pumping lemma proof, this pumping lemma proof I will tell you at the end. Okay, then in the proof you will see why we don't care about strings which are not in the language, why we don't care about the strings whose length is less than p, why we don't care about other things. So basically everything you will see. Okay, so just wait for the proof. Your doubt, I got it, I got your doubt, but your doubt will be answered once we see the proof. Okay, Shivam Bharti is saying that this p, this pumping length, that will be equal to smallest string plus 1. No, that is not correct, Shivam, that is not correct. Okay, don't worry, I will take many examples I will take. Shivam is saying pumping length is equal to smallest string length plus 1. That is wrong. Okay, that is wrong. Don't worry, in the next session it will come. Don't worry, it will come in future. Don't worry. No, any other doubt? Any other doubt? Please tell me. In this session, do you have any other doubt? So tomorrow, after the operating system class, we will continue this pumping lemma part 2. Annotated notes will be available today. Okay, immediately within next 1 hour, I will provide you annotated notes. You can go through the annotated notes. You can revise whatever we have seen in this session. Revise that. Okay, just make sure that you understood small things, everything. Okay, okay, thank you everyone, see you tomorrow. And one more thing, please comment on this video. This video I will put on the Go Classes YouTube channel. Please comment, because this pumping lemma, this is one of those topics which majority of the students, they don't understand. So please comment, please like, and please share. Okay, so one of those topics which can give Go Classes, you know, some publicity. Okay, so you are understanding my point, right? So because scheduling type of topics everyone will teach. Okay, everyone will teach nicely, because that topic is very easy. But this type of topic, scheduling, pumping lemma, decidability, transaction management, synchronization, multi-level paging, this type of topics, they give Go Classes edge. Okay, Go Classes basically in these areas, Go Classes is the expert. So please comment, like, and share. Okay, I will upload this video on YouTube. Please, definitely, please comment. Okay, thank you.